Our capsule descends through clouds that have hidden this world's surface from human eyes for all of history. Layers of sulfuric acid droplets parting reluctantly as we drop toward a landscape no one has ever stood upon. Temperature readings climb steadily on the display, passing 400 degrees Fahrenheit, then 500, then 600, as the descent continues through the dense carbon dioxide atmosphere. Outside the small window, orange light begins to replace the yellowish glow of the cloud layers, and the pressure gauge shows numbers that would crush an unprotected human body instantly. 90 times the atmospheric pressure at Earth's sea level. The heat shield glows faintly from friction, despite the thick atmosphere slowing our fall. And somewhere far below waits the surface of Venus, scorched and ancient and utterly unlike home. The numbers tell one story, measurements and data streaming across screens, but the experience of descending toward this world carries a different weight entirely. We have chosen to visit a place where survival requires technology operating at the absolute edge of what engineering can achieve, where every system must function perfectly, or the environment outside will end everything in moments. The suit waiting in the storage compartment represents years of development, materials that can withstand temperatures hot enough to melt lead, seals that can hold back pressure equivalent to being nearly a kilometer underwater. This journey exists somewhere between what is currently possible and what might become possible, a thought experiment grounded in Venus's real conditions, allowing us to explore what standing on this world would actually mean. You are listening to the Drowsy Astronaut, where we take our time exploring the cosmos through experiences that blend real science with calm immersion. Tonight we descend to Venus and spend a week walking across its surface, observing its landscape and atmosphere and geology, as if the technology existed to make such a journey survivable. If you find yourself settling in for the night, wherever you are, perhaps you might share in the comments where you are listening from and what time it is there. The like button and subscribe option are there if this kind of slow cosmic exploration brings you some quiet fascination. The descent continues through air so thick it behaves almost like a fluid, slowing the capsule naturally without the need for parachutes that would instantly dissolve in the sulfuric acid droplets above. The pressure outside now exceeds 80 Earth atmospheres, and the temperature reading passes 800 degrees Fahrenheit. Heat that would ignite wood and melt many metals if they were exposed directly. The orange glow outside the window brightens gradually, not from fire, but from the diffuse filtering of sunlight through the massive atmosphere. Photons scattered countless times before reaching these lower altitudes. The altimeter counts down steadily. 500 meters above the surface, then 400, then 300. The numbers representing the final approach to a world that has destroyed every spacecraft that tried to land and survive for more than a brief time. At 100 meters, the retro rockets fire briefly, slowing the descent to a gentle settling speed despite the capsule's weight pressing down through the dense air. The surface becomes visible through the window, a rocky plain extending toward a hazy horizon, the stones and regolith appearing dark grey and brown beneath the orange-tinted illumination. 50 meters, then 30, then 20, the ground rising to meet the landing gear, details resolving into individual rocks, and the texture of the surface material between them. Contact occurs with a surprisingly soft bump, the thick atmosphere having cushioned most of the descent energy, and the capsule settles onto its supports with a faint creaking of metal, adjusting to the tremendous external pressure and heat. We have landed on Venus. The first moments sitting inside the capsule involve simply absorbing what the instruments report and what can be seen through the reinforced window. The external temperature stabilizes at 905 degrees Fahrenheit, or 485 degrees Celsius. Hot enough to melt zinc and lead. Hot enough to make many rocks glow faintly if they were in darkness. The pressure reads 92 Earth atmospheres. The weight of all that carbon dioxide pressing down from above with force that would collapse an ordinary building. The composition readings confirm what missions before have measured. 96.5% carbon dioxide, 3.5% nitrogen, traces of sulfur dioxide and other compounds, and absolutely no oxygen, no water vapor, nothing that Earth life could use to breathe or survive. The landscape visible through the window stretches away toward a horizon that appears closer than it would on Earth. Venus's slightly smaller size, creating more pronounced curvature. The lighting has a quality unlike anything experienced on Earth, diffuse and directionless, coming from the entire sky at once, rather than from a single solar disk. Everything appears tinted orange-yellow, the color created by the way light scatters through carbon dioxide at these pressures and temperatures. The wavelengths shifted toward the warm end of the spectrum. No shadows appear beneath the rocks visible near the landing site, or, if shadows exist, they are so soft and faint that they barely register. The scattered light wrapping around obstacles and filling in what would be darkness on Earth. The suit waits in its compartment, and the process of putting it on requires care and methodical checking of every seal and every system. The outer layer consists of materials designed to insulate against the extreme heat, while remaining flexible enough to allow movement. Ceramics and advanced composites, layered in ways that create barriers against both temperature and pressure. The innermost layer maintains comfortable conditions, cooling systems working against the thermal gradient, circulating fluids that carry heat to radiators that somehow manage to reject that heat into an environment already scorching. The helmet seals with multiple redundant gaskets, and the faceplate uses materials that can withstand both the heat and the chemical exposure to sulfuric compounds in the air. Gloves and boots complete the ensemble, each piece tested countless times, but never in conditions quite as extreme as what waits outside. The final checks take longer than they should, because rushing here would be foolish. Every connection verified, every pressure seal confirmed, every system showing green status before proceeding. The suit's internal atmosphere reads as normal Earth air, 14.7 pounds per square inch, 21% oxygen, comfortable temperature, humidity controlled, a bubble of home carried in a shell designed to survive hell. The external sensors on the suit confirm what the capsule measured. Over 900 degrees outside, 92 atmospheres of pressure, air composition that would kill in seconds even if the heat and pressure did not. Everything indicates the suit should protect against all of these hazards, should allow hours of surface exploration before requiring return to the capsule to recharge cooling and air systems. The airlock cycle takes several minutes, the small chamber first matching the capsule's internal pressure, then slowly increasing pressure to match the outside environment. The suit compresses slightly around the body as external pressure builds, the materials designed to distribute the force evenly, but the sensation of being squeezed intensifies until it stabilizes at 92 atmospheres. Temperature inside the suit rises slightly, despite the cooling systems working at full capacity. Not dangerously, but noticeably, a reminder of the thermal environment just centimeters away from the body. The airlock's outer door unlocks with a heavy clunk that transmits through the thick air as a deep, low-frequency sound, and the door swings open to reveal the Venusian landscape in full, unfiltered view. Stepping out onto the surface requires a moment of psychological adjustment, of accepting that the boot, now pressing against Venusian rock, is separated from 900-degree heat by only the suit's material layers. The ground feels solid, not dusty or soft, but firm like stepping on earth rock. The regolith, compacted by the weight of the atmosphere, pressing down on it for millions of years. The suit's weight feels different here. Venus's gravity pulling at 90% of Earth's strength, making movement feel almost normal. Not the bouncing lightness of the moon, but something close to familiar. The first step away from the airlock carries symbolic weight, becoming the first human footprint on Venus's surface if this journey were real. A mark that would persist for millions of years in the absence of wind or water to erase it. The immediate surroundings extend perhaps 20 or 30 meters before details begin to blur into the orange haze. The thick atmosphere scattering light and limiting visibility despite the relatively clear air near the surface. Rocks of various sizes lie scattered across the plain, ranging from pebbles to boulders the size of vehicles, all appearing dark grey or brown beneath the orange illumination. The ground between the rocks consists of fine-grained material. Regolith, created by the slow chemical weathering of rock surfaces, and the occasional micrometeorite impact that makes it through the thick atmosphere. No plants grow here, no lichens cling to the rocks, no insects move across the ground. The absolute sterility of a world where life as Earth knows it cannot exist. The sky overhead shows the source of the orange light, a glowing expanse without clear features. No visible sun or clouds from this vantage point beneath the main cloud deck. The glow comes from everywhere and nowhere, as if the entire sky were a diffuse light source. Sunlight scattered through 50 kilometers of atmosphere and haze between the surface and the sulfuric acid clouds above. The color shifts subtly across the sky, perhaps slightly brighter in one direction where the sun might be. But the thick air prevents any direct view, reducing the star that powers all this to a general brightening of one portion of the orange dome. Looking up creates a sense of being at the bottom of an ocean of air, the weight of it pressing down, the light filtering through from impossibly far above. Sound travels strangely in the dense carbon dioxide atmosphere, the suit's external microphones picking up vibrations that the internal speakers translate into something the human ear can process. Footsteps create low, deep thuds rather than the crisp sounds they would make on Earth. The frequency shifted downward by the different properties of carbon dioxide at high pressure. Tapping a rock with a gloved hand produces a sound like tapping stone underwater, muffled and altered. the vibrations traveling through the thick air differently than through Earth's nitrogen-oxygen mixture. The overall acoustic environment feels muted and strange, sounds dampened and changed, adding to the alien quality of this place. The suit's systems report normal operation, cooling, keeping pace with the heat, trying to penetrate from outside, the pressure differential between inside and outside, holding steady at the seals, air supply and power reserves showing hours of capacity remaining. These readings provide constant reassurance that survival continues moment by moment, that the technology functions as designed despite the hostile environment. The internal temperature reads a comfortable 72 degrees Fahrenheit, while the external sensor, mere centimeters away, reads 905 degrees. A gradient of over 800 degrees across a few inches of advanced materials. The suit makes survival possible, but the constant awareness of what waits just beyond the protective layers creates a background tension. Not fear exactly, but deep respect for this environment's power. The horizon draws attention repeatedly. That boundary where the orange-lit ground meets the orange glowing sky. A circle, perhaps 3 kilometers away, in every direction. On Earth, the horizon at ground level extends nearly 5 kilometers, but Venus's smaller radius and the atmospheric haze combine to limit the visible distance to about 3/5 of Earth's horizon range. Everything beyond that boundary fades into the orange murk, features becoming indistinct and then invisible, creating the impression of standing in a relatively small bubble of visibility surrounded by infinite haze. This limited view makes the landscape feel simultaneously confined and vast. The knowledge that plains extend for hundreds of kilometers, contrasting with the inability to see more than a few kilometers in any direction. Walking a short distance from the lander allows observation of how the landscape responds to movement, or rather, how it does not respond. The rocks do not shift, the ground does not yield, no dust rises into the air, because the atmosphere's density and the absence of wind mean particles settle immediately if disturbed. Kicking at a small stone sends it tumbling a short distance before it comes to rest, the motion looking slow and deliberate despite the near-Earth gravity, the dense air providing significant resistance to movement. Everything feels weighted and substantial, motion requiring more effort than on Earth despite the slightly lower gravity. The thick atmosphere creating drag on every action. The quality of being here, of standing on another world's surface, brings a strange mixture of familiarity and alienness that shifts back and forth with attention. The rocks look like rocks, the ground looks like ground. The basic visual experience of a rocky landscape reads as something understandable and relatable. But then the orange light registers, or the temperature display catches the eye, or the suit's cooling system hums slightly louder as it works against the heat, and the alienness reasserts itself. The reminder that this place operates under rules different from Earth's. The mind oscillates between these two states, sometimes seeing just a rocky plain, sometimes seeing a vision of hell made solid, the truth lying somewhere between these extremes. Returning attention to the immediate area around the landing site reveals details that were not apparent during the initial survey. Individual rocks show textures on their surfaces, tiny pits and irregularities created by chemical interactions with the atmosphere over millions of years. Some rocks appear to have thin coatings of different material, possibly minerals deposited from atmospheric gases. reacting with the stone surfaces. The regolith shows variation in grain size, some areas finer than others. Patterns perhaps created by ancient lava flows that spread across this region hundreds of millions of years ago, and then weathered slowly into the current surface. A small impact crater, perhaps 2 meters across, sits about 10 meters from the lander, its rim slightly raised above the surrounding plain, its interior bowl-shaped and unremarkable. Impact craters on Venus are less common than on airless worlds, because the thick atmosphere burns up smaller meteorites before they reach the surface. But larger objects still make it through and excavate craters when they strike. This particular crater could be thousands of years old or millions of years old. The slow weathering rates making age determination difficult without detailed analysis. The crater's existence reminds us that this plane, stable as it appears, occasionally receives violent visitors from space, though far less frequently than the Moon or Mercury. The first extended period on Venus's surface, these initial hours of observation and adjustment, creates a foundation of experience that will inform everything that follows during the week ahead. The environment's basic parameters become familiar through repeated exposure. The heat held back by the suit, the pressure requiring the systems to maintain internal conditions, the orange light creating the visual baseline, the limited horizon defining the observable range, the silence and stillness pervading everything. These constants will remain throughout the journey, the background against which variations and discoveries will stand out. And understanding them thoroughly now makes later observations more meaningful. The landscape surrounding the landing site extends in all directions as a relatively flat volcanic plain. One of the most common terrain types on Venus, and the reason this location was chosen for the touchdown, volcanic plains cover about 80% of Venus's surface. Vast regions where ancient lava flows spread across the planet and then solidified into the bedrock that now forms the foundation of the visible landscape. These plains are not perfectly flat, but gently undulating, with variations in elevation of only meters across distances of kilometers, creating subtle swells and shallow depressions that become apparent only when traversing them or studying detailed topographic data. The rocks scattered across the surface near the lander show characteristics consistent with basaltic composition, the same type of volcanic rock that forms Earth's ocean floors and many of its volcanic regions. Basalt forms when lava cools relatively quickly, creating fine-grained rock with small crystals rather than the large crystals that form when magma cools slowly underground. The rocks here appear dark grey where fresh surfaces are visible, though most surfaces show the brownish weathered coating created by long exposure to Venus's atmosphere. Breaking one rock open, if that were possible, would likely reveal the darker, unweathered interior, the original volcanic material, unchanged since it solidified from lava, perhaps 500 million years ago. The size distribution of the rocks follows a pattern common to volcanic plains, with many small rocks and fewer large ones. The smaller fragments likely created when larger rocks fractured due to thermal stresses as they cooled, or later split from temperature, cycling over millions of years. The temperature on Venus changes little between day and night, but over geological timescales, even small variations can stress rock until it fractures, especially if the rock contains different minerals that expand and contract at different rates. Some rocks show angular shapes with sharp edges, while others appear more rounded. Though the rounding comes not from water or wind erosion, but from chemical weathering that slowly dissolves and redistributes material from the surface. The largest boulder visible from the landing site sits about 50 meters to the east, a dark mass, perhaps 3 meters high and 5 meters across at its base, resting on the plain like an ancient monument. Walking toward it requires about 100 steps through the thick atmosphere, each step feeling deliberate as the suit pushes through air dense enough to create noticeable resistance. The boulder becomes clearer as the distance closes, its surface showing the same brownish weathered coating as the smaller rocks, but also displaying what appear to be flow textures, patterns suggesting this particular mass was part of a lava flow that solidified while still moving. The textures resemble features seen in basaltic lava flows on Earth, where the surface cools and forms a skin, while the interior remains liquid, creating ropey or billowed patterns that freeze into the solid rock. Standing next to the boulder provides scale and perspective. The human figure in the bulky suit reaching perhaps to the middle of the boulder's height. The rock mass, representing tons of solidified lava that has rested in this location for hundreds of millions of years. The boulder shows no signs of having been moved or disturbed since it solidified, no evidence of rolling or tumbling that would create impact marks or fresh fractured surfaces. It likely sits very close to where it formed as part of a lava flow, or possibly it represents a large fragment ejected from a volcanic vent and landed here, though the lack of a nearby crater makes the lava flow origin more probable. The ground immediately around the boulder consists of finer regolith than the areas farther away, possibly because the boulder itself has weathered and contributed material to the surrounding surface, or possibly because wind patterns in Venus's ancient past, when the atmosphere was different, concentrated fine particles in this location. The regolith feels firm underfoot, not dusty or loose, but compacted, pressing back against the boot with solid resistance. Scraping at the surface with a gloved hand disturbs only the top few millimeters, revealing that beneath the loose surface layer, the material becomes increasingly compacted, compressed by the weight of the atmosphere and the long ages of settling. Moving away from the boulder toward the northern edge of the visible area reveals more of the same general terrain, volcanic plains with scattered rocks and very gentle variations in elevation. A slight rise becomes apparent about 200 meters north of the lander, the ground sloping upward perhaps 2 or 3 meters over that distance, creating a subtle swell that would be almost unnoticeable on Earth, but stands out here in the otherwise flat landscape. Walking up the gentle slope provides a marginally elevated viewpoint, though the gain in altitude is so small that the horizon distance increases by only tens of meters. From this slightly raised position, the landscape spreads out in all directions, plains extending to the hazy limits of visibility, with no dramatic features breaking the monotony. The view back toward the lander from this elevated position shows the spacecraft sitting on the plain, with its landing gear firmly planted, the metallic surfaces already showing discoloration from the brief exposure to Venus's atmosphere. The heat and chemical environment attack any exposed metal, and even advanced alloys designed to resist corrosion show changes within hours of exposure. The lander was never designed for long-term survival on the surface. Its mission timeline measured in days, not years. and already the environment begins the slow process of degradation that will eventually reduce it to a weathered husk. This visual reminder of the environment's hostility creates appreciation for the suit's continued function. The systems that maintain survivable conditions, despite the same heat and chemistry attacking every external surface. To the south, the terrain appears even flatter than to the north, the plain extending without visible variation toward the orange horizon. A few larger rocks punctuate the landscape at various distances, dark shapes rising slightly above the general surface level, but no dramatic features appear. No mountains or hills or cliffs, just the gentle undulation of volcanic plains that could extend for hundreds of kilometers in this condition. This flatness characterizes much of Venus's surface, the volcanic resurfacing having filled in older topography and created the smooth plains that dominate the landscape. Only in certain regions do mountains and highland areas rise above these plains, and those features lie far beyond the current visible range. The western view shows similar terrain, though a concentration of larger rocks, about 300 meters away, creates a slightly rougher area, possibly the edge of a different lava flow, or a region where the surface fractured and created more abundant rock fragments. Reaching that area would require a deliberate trek across the intervening plain, a journey to consider for later exploration when the immediate surroundings have been more thoroughly observed. The eastern view completes the circle, revealing the boulder already visited, and beyond it, more plains fading into haze, the uniformity broken only by scattered rocks and the very gentle terrain variations. Returning to the area immediately around the lander allows closer examination of features too small to notice from a distance. The regolith between rocks shows subtle textures, tiny ripples and patterns whose origin remains unclear, possibly created by settling processes, or perhaps the result of ancient atmospheric conditions different from today's. The surface color varies slightly from place to place, some areas appearing darker gray and others tending toward brown. The variations possibly indicating different degrees of weathering or slightly different mineral compositions in the source rocks. These subtle differences would be invisible in photographs taken from orbit, detectable only through direct observation at ground level. Small impact craters dot the landscape at irregular intervals, most only centimeters or tens of centimeters across, created by micrometeorites that survived passage through the thick atmosphere and struck the surface with enough energy to excavate tiny craters. These smallest craters show sharp rims and bowl-shaped interiors. Their small size, meaning they have not had time to degrade significantly through weathering, despite their potential ages of millions of years. Larger craters, those meters or tens of meters across, are less common but more obvious, their rims rising slightly above the surrounding terrain, and their interiors sometimes filled partially with fine regolith. One such larger crater sits about 100 meters southwest of the lander, perhaps 5 meters in diameter, with a rim raised about half a meter above the plain. Walking over to investigate provides opportunity to observe how craters form in this environment and how they age over time. The rim shows the characteristic structure of impact craters, material thrown outward during the excavation process and piled up around the rim, creating the raised circular wall. The interior slopes down to a floor about 2 meters below the rim, the bowl shape typical of small to medium impact craters. Fine regolith has accumulated in the crater floor, possibly material that has slowly settled from the atmosphere or weathered from the crater walls, partially filling what was originally a deeper depression. The crater walls show layering in the exposed material, different levels of regolith and rock visible in cross-section, providing a glimpse into the subsurface structure. The top layer consists of loose regolith, perhaps 30 centimeters thick, beneath which appears more compacted material, and below that, what might be solid bedrock, though the transitions between layers are gradual rather than sharp. This layering suggests the history of surface processes, the accumulation of material over time. The compaction of lower layers under the weight of material above, the slow transformation of loose particles into more coherent deposits. The crater has cut through these layers and exposed them, creating a natural cross-section through the surface geology. Walking around the crater rim provides views of the interior from different angles, though the variations are subtle, all showing the same basic bowl shape and the accumulated regolith in the floor. No rocks protrude from the crater walls or litter the floor, suggesting the impactor that created this crater was smaller than the crater itself, as is typical. The explosion of impact vaporizing the incoming object and excavating material from the target surface to create a crater many times the impactor's size. The crater's age remains uncertain without detailed analysis, but the moderate degradation of the rim and the partial filling of the interior suggest it is ancient, perhaps tens or hundreds of millions of years old. Young by Venus standards, but old compared to similar features on Earth that would have eroded away completely in such timescales. The position of the crater relative to the lander was likely coincidental. The random distribution of impacts across the surface, meaning some areas have higher crater densities than others, purely by chance. The crater provides a landmark, a recognizable feature in the otherwise relatively uniform landscape, and its presence adds variety to the immediate surroundings. Using it as a reference point, the lander sits to the northeast, the large boulder to the east, the slight rise to the north, and the rough area with many rocks to the west, creating a mental map of the landing site area that will serve as the baseline for understanding this location on Venus. The regolith covering the plain deserves closer attention, as it represents the surface material created by millions of years of weathering and impact processes. Scooping up a handful, if the suit's gloves allowed such fine manipulation, would reveal material ranging from dust-fine particles to grains a few millimeters across, a mixture of sizes created by different processes. The finest dust likely comes from chemical weathering, minerals slowly altered by reactions with sulfur compounds and other atmospheric constituents, breaking down into tiny particles. Larger grains probably formed from physical weathering, rocks fracturing from thermal stress or impact, and breaking into progressively smaller fragments over time. The color of the regolith tends toward brownish gray, darker than the bright red soils of Mars, but not as dark as lunar regolith. The color reflecting the basaltic composition and the weathering products that form on exposed surfaces. The material shows no sign of moisture or ice, no clumping or cohesion beyond what the atmospheric pressure provides by pressing particles together. Disturbing the regolith with a boot leaves a clear impression. The fine particles displaced by the boot's pressure and the thick atmosphere preventing any dust from rising into the air. The impression remains sharp-edged after the boot lifts away, a mark that will persist until some future event disturbs it, whether another impact or seismic activity, or the gradual accumulation of settling particles over millions of years. These details of the landing site, the rocks and regolith and small craters and subtle terrain variations create the immediate context for the Venus surface experience. This particular spot on the vast plains could be almost anywhere on the volcanic regions that cover most of the planet, representative of the most common Venusian terrain. Understanding this baseline makes variations encountered during later exploration more meaningful, providing the standard against which differences can be measured. The landing site becomes familiar through this thorough observation, no longer just a landing zone, but a known place with specific characteristics, the starting point for the week-long journey across this extraordinary world. Above the landing site and the surrounding plains stretches the atmosphere that makes Venus unique among the terrestrial planets. A massive envelope of gas pressing down with crushing force and trapping heat with ruthless efficiency. Looking upward from the surface means looking through more than 90 kilometers of atmosphere, though the bulk of the mass concentrates in the lower layers, with the pressure decreasing exponentially with altitude, according to the same physical principles that govern Earth's atmosphere, but operating in a much more extreme environment. The atmosphere here is not merely air to breathe or weather to experience, but a dominant presence, a massive system that shapes every aspect of this world's character. The composition consists overwhelmingly of carbon dioxide, making up 96.5% of all molecules in the air, with nitrogen providing most of the remaining 3.5%, and trace gases, including sulfur dioxide, water vapor, carbon monoxide, and other compounds present in very small amounts. This carbon dioxide dominance creates conditions utterly unlike Earth's nitrogen-oxygen atmosphere, with different density, different heat capacity, different optical properties, different chemical behaviors. The pressure at the surface, 92 times Earth's sea level pressure, results from the sheer mass of carbon dioxide above. The atmospheric column weighing far more per unit area than Earth's atmosphere, despite Venus being a slightly smaller planet. This tremendous pressure creates an environment where gases begin to behave with properties intermediate between normal gases and liquids. The carbon dioxide at the surface having a density about 6.5% that of water, dense enough to provide significant buoyancy to objects, and dense enough to transmit sound very efficiently at low frequencies. The pressure also raises the temperature required to boil liquids, though with surface temperatures already at 900 degrees Fahrenheit, nothing liquid exists at the surface under current conditions. The combination of pressure and temperature puts the surface atmosphere in what physicists call a supercritical state for carbon dioxide, where the distinction between gas and liquid phases blurs and the material shows properties of both. The mass of atmosphere above the surface totals about 90 times more per square meter than on Earth, creating the tremendous pressure that requires the suit structure to be so robust. If the atmospheric mass were distributed evenly around the planet, it would create a layer of carbon dioxide gas extending from the surface to an altitude of about 15 kilometers at Earth's surface pressure, or compressed to only about 200 meters thick if somehow squeezed to the density of solid carbon dioxide ice. The actual atmosphere extends far higher than 15 kilometers because pressure and density decrease with altitude, allowing the upper reaches to extend to altitudes of several hundred kilometers before the atmosphere becomes too thin to measure. Though the useful atmosphere where significant density exists, occupies the lowest 100 kilometers or so. The temperature structure of the atmosphere varies dramatically with altitude, creating distinct layers much as Earth's atmosphere separates into troposphere, stratosphere, and higher regions. At the surface, temperatures reach 475 degrees Celsius, maintained at this scorching level by the greenhouse effect that traps infrared radiation beneath the thick clouds. Rising upward through the lower atmosphere, temperature decreases gradually, dropping to about 360 degrees Celsius at 10 kilometers altitude. Still hot enough to melt lead, but noticeably cooler than the surface. The temperature continues falling with altitude, reaching about 70 degrees Celsius at 40 kilometers altitude, approximately the temperature of a hot summer day on Earth, and cool enough that humans could survive in a pressure suit without active cooling. At 50 kilometers altitude, temperatures drop to near freezing, and here the main cloud deck begins, a layer of sulfuric acid droplets that extends from about 48 kilometers to about 70 kilometers altitude. The clouds form through complex chemistry involving sulfur dioxide and water vapor in the upper atmosphere, with ultraviolet light from the sun breaking molecules apart and allowing them to recombine into sulfuric acid, which then condenses into tiny droplets that make up the cloud particles. These droplets remain suspended in the middle atmosphere, circulating in the fierce winds that blow at these altitudes, sometimes falling through the lower boundary of the cloud deck and evaporating in the hotter air below, sometimes rising through the upper boundary and evaporating in the colder, drier air above. The clouds are responsible for Venus's bright appearance when viewed from Earth or from space, reflecting about 75% of the sunlight that hits them back into space before it can reach the surface. This high reflectivity makes Venus the brightest planet in Earth's sky and gives it a dazzling white appearance from above the clouds, hiding the orange-brown surface completely from external view. From below the clouds, looking up from the surface, the cloud deck appears as the upper boundary of the visible atmosphere. A ceiling above which conditions remain hidden, but from which light filters down through tens of kilometers of clear air to reach the ground. Between the surface and the cloud deck lies a relatively clear region of atmosphere, though clear in this context means free of cloud droplets, not transparent in the way Earth's air can be transparent. The carbon dioxide air itself scatters light effectively, creating the haze that limits visibility even on a cloudless day, and various particles suspended in the lower atmosphere contribute additional scattering. These particles may include fine sulfur compounds, small amounts of chlorine and fluorine compounds outgassed from volcanic activity, and possibly tiny droplets or crystals that form in the cooler upper reaches of the lower atmosphere before evaporating in the heat closer to the surface. The result is air that is nominally clear but optically thick, reducing visibility to a few kilometers at most. The greenhouse effect operating in this atmosphere represents one of the most extreme examples in the solar system, a cautionary demonstration of what happens when atmospheric composition shifts to maximize heat trapping. The mechanism begins with sunlight penetrating the clouds and reaching the surface, where the visible and near-infrared light is absorbed by the rocks and regolith, heating them to temperatures that would be much lower if the atmosphere were thin or transparent to infrared radiation. The hot surface then radiates infrared light upward, as all warm objects do. But carbon dioxide molecules absorb infrared radiation very effectively at specific wavelengths, capturing the energy and preventing it from escaping to space directly. The absorbed infrared energy warms the carbon dioxide molecules, which then emit infrared radiation in all directions, including back downward toward the surface, creating a blanket effect where heat is trapped in the lower atmosphere and surface region. The thick cloud deck adds to this effect by reflecting infrared radiation back downward and by acting as an additional layer of insulation, preventing heat from escaping to space. The combination of carbon dioxide absorption and cloud layer insulation creates surface temperatures far higher than would exist based on Venus's distance from the Sun alone, demonstrating how atmospheric composition can overwhelm other factors in determining planetary climate. Comparing Venus's greenhouse effect to Earth's shows the difference in scale. Earth's natural greenhouse effect raises surface temperature by about 33 degrees Celsius above what it would be without an atmosphere, making the difference between a frozen world and a habitable one, while Venus's greenhouse effect raises temperatures by about 460 degrees Celsius above the airless baseline, creating the difference between a possibly habitable world and an oven. The difference results primarily from the amount of carbon dioxide in the atmosphere. Venus, having almost 200,000 times more carbon dioxide than Earth's atmosphere. Despite the planets being similar in size, the carbon dioxide on Earth being mostly locked up in carbonate rocks rather than existing as atmospheric gas. The question of how Venus acquired such a massive carbon dioxide atmosphere and lost its water connects to the planet's history and its proximity to the Sun. Early in solar system history, Venus may have had liquid water oceans similar to Earth, with most of its carbon dioxide dissolved in the oceans or locked in carbonate rocks on the seafloor. As the Sun gradually brightened over billions of years, Venus received increasing amounts of solar radiation, warming the surface and increasing ocean evaporation. Water vapor is itself a greenhouse gas, so increased water vapor in the atmosphere trapped more heat, causing more evaporation in a runaway feedback loop. Eventually, the oceans evaporated completely, and without liquid water to dissolve carbon dioxide or form carbonate rocks, volcanic outgassing released carbon dioxide into the atmosphere, where it accumulated over geological time. The water vapor in the upper atmosphere was broken apart by solar ultraviolet radiation into hydrogen and oxygen, with the lightweight hydrogen escaping to space while the oxygen reacted with surface rocks, gradually stripping Venus of its water over hundreds of millions of years. The end result left Venus with a massive carbon dioxide atmosphere, almost no water, and surface temperatures high enough to prevent liquid water from ever condensing again, even if water somehow returned to the atmosphere. This history suggests Venus may have been more Earth-like early in its history, potentially habitable, before the runaway greenhouse effect transformed it into the scorched world we see today. The upper atmosphere, above the cloud deck, extends to altitudes of several hundred kilometers before transitioning into space, with temperature and density decreasing steadily with altitude in these highest regions. The thermosphere, above about 120 kilometers altitude, experiences heating from solar ultraviolet and X-ray radiation, with temperatures rising again to several hundred degrees Celsius, though the air is so thin at these altitudes that the high temperature doesn't represent much heat energy. The exosphere, the outermost layer, begins around 200 to 300 kilometers altitude, where the atmosphere becomes so diffuse that particles can travel many kilometers without colliding with other particles. And some particles moving fast enough can escape Venus's gravity and be lost to space, continuing the slow atmospheric erosion that has been occurring for billions of years. The atmosphere's circulation patterns create the dramatic superrotation observed at cloud level, where the entire atmosphere circles the planet in about 4 Earth days, while the solid planet beneath rotates only once every 243 Earth days. This means the atmosphere moves about 60 times faster than the surface, creating winds at cloud level that reach speeds of 100 meters per second, roughly 360 kilometers per hour, or 225 miles per hour, faster than the strongest hurricanes on Earth. The mechanism driving this superrotation remains not entirely understood, involving complex interactions between solar heating, the planet's slow rotation, and the transfer of angular momentum within the atmosphere, creating a system where the atmosphere has essentially decoupled from the solid planet's rotation and established its own faster rotation rate. At the surface, however, these dramatic winds are almost imperceptible. The thick, dense air moving at only a few kilometers per hour at most, too slow to create the sensation of wind despite the enormous speeds aloft. The density of the surface air means even slow winds carry significant momentum and energy, but the resistance to flow prevents the rapid movements seen at higher altitudes from penetrating to ground level. The result is a paradox, where the planet has one of the most dynamic atmospheres in the solar system in terms of circulation speed. Yet, the surface experiences near-calm conditions, the massive atmospheric pressure acting as a damper that suppresses surface winds and creates a still, quiet environment punctuated only by very gentle air movements. This atmospheric system, from the scorching surface through the cloud layers to the upper atmosphere's tenuous wisps, creates the environment that defines Venus and makes it simultaneously fascinating and hostile. Understanding what lies overhead, even though most of it remains invisible from the surface, provides context for the conditions experienced at ground level and explains why this world evolved so differently from Earth, despite their similar sizes and rocky compositions. The atmosphere is not merely a feature of Venus, but its defining characteristic, the reason this planet appears the way it does, and the barrier that must be overcome for any surface exploration to succeed. Beneath the boots, through the suit's protective sole, the ground presses back with the solid firmness of ancient rock, a foundation that has existed for hundreds of millions of years and will likely persist for hundreds of millions more, barring catastrophic volcanic resurfacing. The rocks and regolith covering the surface here represent the accessible face of Venus's geology, the topmost layer of a planet that extends nearly 6,400 kilometers to its iron core. But these surface materials tell stories about volcanic processes and planetary evolution that reach deep into Venus's history. Understanding what these rocks are made of and how they came to be here requires looking closely at their composition, texture, and the processes that created them. The dominant rock type across most of Venus's surface appears to be basalt, the same volcanic rock that forms Earth's ocean floors and many of its volcanic islands and continental flood basalts. Basalt forms when lava with relatively low silica content erupts and cools, creating rock composed primarily of minerals like pyroxene and plagioclase feldspar, with smaller amounts of olivine and other minerals depending on the exact composition of the source magma. The lava that created these basalts likely came from partial melting of Venus's mantle. The thick, rocky layer between the crust and the metallic core, with the molten rock rising through fractures and vents to reach the surface where it flowed across the landscape before cooling and solidifying. The basaltic composition is inferred from several lines of evidence, including measurements made by Soviet Veneralanders in the 1970s and 80s, which analyzed surface rocks using X-ray fluorescence and gamma-ray spectroscopy. These measurements showed silica content around 45 to 50% by weight, magnesium oxide around 10 to 15%, calcium oxide around 7 to 10%, aluminum oxide around 15 to 17%, and iron oxide around 8 to 10%, values consistent with basaltic or slightly more primitive compositions. The measurements came from different landing sites across the planet, suggesting basalt is widespread, though some highland regions showed compositions closer to granite or andesite, rocks with higher silica content that form through different processes. The rocks visible near the landing site showed textures consistent with basaltic lava that cooled relatively quickly, creating fine-grained material where individual mineral crystals are too small to see without magnification. Some rocks show vesicles, small holes created when gas bubbles were trapped in the cooling lava. The bubbles marking places where volcanic gases, like sulfur dioxide or carbon dioxide, were dissolved in the molten rock at depth, but came out of solution as the lava reached the surface and pressure dropped. The vesicles give some rocks a spongy appearance, the holes ranging from millimeters to centimeters across, distributed randomly through the rock volume, or sometimes concentrated near the surface where the lava first contacted the atmosphere. The surfaces of the rocks show weathering that has altered their appearance from the fresh, dark grey of newly erupted basalt to the brownish tones visible on most exposed surfaces here. This weathering occurs not through water, which no longer exists as liquid on Venus's surface, but through chemical reactions between the rock minerals and atmospheric gases, primarily sulfur dioxide and other sulfur compounds. At the high surface temperatures, these reactions proceed faster than they would at Earth's surface temperatures, but still slowly enough that weathered coatings take thousands or millions of years to develop to noticeable thickness. The brown color likely comes from iron compounds in the rock, reacting with sulfur to form iron sulfide minerals, like pyrite, or with oxygen to form iron oxide minerals, like hematite, both of which can create brownish colorations. Some rocks show what appear to be thin coatings or rinds on their surfaces, layers perhaps millimeters thick, with different color or texture than the underlying rock, possibly representing the altered zone where atmospheric gases have reacted most intensely with the surface minerals. Breaking a rock open, if tools were available to do so, would likely reveal the transition from weathered outer layer to fresh interior, the coating thickness potentially providing information about how long the rock surface has been exposed to the atmosphere. Rocks buried beneath regolith would show weathering only on previously exposed surfaces, while rocks that have rested on the surface continuously since the lava solidified would show weathering on all sides. The regolith itself, the loose material covering the solid bedrock, consists of fragments ranging from dust-fine particles up to pebble-sized pieces. all derived from the breakdown of bedrock through weathering and impact processes. On an airless world like the Moon, regolith forms primarily through micrometeorite bombardment, the constant rain of tiny impactors grinding rock into progressively finer particles. But on Venus, the thick atmosphere burns up most small impactors before they reach the surface. So micrometeorite gardening contributes less to regolith formation than on the Moon. Instead, chemical weathering and thermal stress fracturing likely dominate regolith formation, slowly breaking down rock surfaces into particles that accumulate over time. The grain sizes in the regolith show a distribution pattern where smaller particles are more abundant than larger ones, following a mathematical relationship common to many geological processes where fragmentation produces fewer large pieces and many small pieces. The smallest particles, those in the dust size range below about 60 microns in diameter, make up a significant fraction of the regolith volume, these tiny grains settling slowly through the dense atmosphere and coating all surfaces with a fine layer. The dust gives the surface a slightly dusty appearance, despite the atmosphere preventing it from rising into clouds, and handling regolith, if the suit's gloves allowed such interaction, would likely result in dust coating the glove surfaces and requiring cleaning. The color of the regolith, brownish-gray in the orange light, would appear different under white light, possibly showing more of the gray tones typical of basaltic material, with the brown weathering products creating a subtle tint. Some regolith samples might show reddish or orange tints from iron oxides, while others might appear darker from iron sulfides or from the presence of fresh, unweathered basalt particles. The variation in color creates subtle patterns across the landscape, some areas appearing slightly darker or lighter than others, variations that likely reflect different source rocks, different weathering histories, or different degrees of regolith maturity and evolution. Beneath the regolith layer lies the bedrock, the solid foundation of coherent rock that forms Venus's crust. Though how deep one must dig to reach bedrock from the surface likely varies from place to place, depending on local geological history. In areas of very old lava flows, the regolith might have developed to depths of meters over hundreds of millions of years, while in regions of younger flows, the regolith might be thin or even absent in places where bedrock outcrops at the surface. The bedrock itself represents the frozen remains of lava flows that spread across this region during Venus's most recent major resurfacing event, an episode of intense volcanism that appears to have covered most of the planet, with fresh lava between 300 and 700 million years ago. This resurfacing event, inferred from the relative scarcity of impact craters on Venus's surface, and from the age distribution of craters that are present, suggests the planet underwent a catastrophic period of volcanic activity that buried most of the previous surface under hundreds of meters or even kilometers of new lava. The mechanism that triggered such intense, widespread volcanism remains debated among planetary scientists, with theories ranging from the catastrophic overturn of Venus's mantle to the gradual buildup of heat beneath a thick, immobile crust that eventually broke apart and allowed massive eruptions, to the possibility that Venus undergoes cycles of intense volcanism separated by long quiet periods, and we are currently in a quiet period following the most recent active phase. The bedrock composition, primarily basaltic according to the available measurements, tells us about Venus's interior composition and the processes occurring in the mantle where these rocks originated. Basaltic magmas form when mantle rock, composed mainly of the minerals olivine and pyroxene, undergoes partial melting, with about 10 to 30% of the mantle rock melting and separating from the solid remainder. This partial melting occurs when mantle rock rises toward the surface and pressure decreases, allowing minerals with lower melting points to melt, while minerals with higher melting points remain solid, creating a basaltic liquid and leaving behind a more magnesium-rich solid residue. The basaltic liquid, being less dense than the solid mantle, rises through cracks and eventually erupts at the surface. The presence of basaltic rocks over most of Venus suggests the planet's mantle composition is similar to Earth's mantle, at least in the upper layers where partial melting occurs. This similarity makes sense given that Venus and Earth have similar sizes and densities, and likely formed from similar materials in the early solar system. The differences in surface conditions between the two planets arise not from different internal compositions, but from different atmospheric evolution and different tectonic processes. With Earth's plate tectonics constantly recycling crust, while Venus appears to lack plate tectonics and instead resurfaces through episodic volcanic events. Some regions on Venus, particularly the highland areas like Ishtar Terra, show rocks with compositions different from basalt, with higher silica content approaching granite or andesite compositions. These rocks suggest more complex volcanic processes, possibly involving remelting of existing crust to produce more silica-rich magmas, or possibly representing continental-type crust that formed early in Venus's history and survived the later basaltic resurfacing events. The presence of these different rock types adds diversity to Venus's geology and suggests the planet has experienced varied geological processes over its history. Not just simple basaltic volcanism, but more complex magmatic evolution. The volcanic features visible in orbital radar images, the shield volcanoes and pancake domes and complex coronae structures, provide additional evidence of varied volcanic processes. Shield volcanoes form when low viscosity lava erupts relatively gently and flows long distances before solidifying, building broad dome-shaped mountains with gentle slopes. While pancake domes form when more viscous lava erupts and cannot flow far, creating steep-sided circular domes with flat tops. Coronae, large circular to oval features surrounded by concentric rings of fractures, likely form when mantle plumes rise beneath the crust and partially melted, creating volcanic activity and deformation at the surface that produces the characteristic circular patterns. Each of these feature types represents different volcanic processes and different magma compositions, creating the geological diversity visible from orbit, even though all the rocks ultimately derive from Venus's mantle. Understanding the composition and origin of the rocks underfoot provides foundation for understanding Venus's geological evolution and its similarity to and difference from Earth. The basaltic plains represent the most recent chapter in a long geological history, the current surface that buries older surfaces and hides them from view. What lies beneath these basalts, what Venus's crust looked like before the most recent resurfacing, remains largely unknown, accessible only in the highland regions where older rocks possibly survived the volcanic onslaught. This partial knowledge creates both satisfaction at understanding the present and curiosity about the hidden past, the earlier Venus that may have been wetter, cooler, and more Earth-like before the runaway greenhouse transformed the climate and potentially before catastrophic volcanism erased much of the evidence. The ground beneath the suit holds these secrets, each rock a piece of evidence about processes that shaped this world over billions of years. Kneeling to examine a particular rock more closely reveals details invisible from standing height. The texture of the weathered surface showing tiny pits and grooves created by chemical alteration, the vesicles creating a pattern that records how gases escaped from the cooling lava. Some areas of the rock show what might be mineral crystals, small reflective facets catching the orange light, possibly pyroxene or plagioclase crystals that grew large enough to see individually, indicating this particular rock cooled slightly more slowly than the fine-grained material surrounding it. The rock feels solid through the suit's gloves, unyielding, the hardness of basalt at these temperatures making it as strong as concrete or stronger. The thermal properties of the rocks themselves contribute to the surface environment, as the rocks absorb heat during the day and release it at night. Though the day-night temperature variation on Venus is minimal due to the thick atmosphere redistributing heat globally, the rock surfaces reach temperatures in equilibrium with the surrounding air, about 900 degrees Fahrenheit, or 475 degrees Celsius, hot enough to glow faintly red if observed in complete darkness. Though the orange atmospheric glow prevents seeing this thermal emission. Touching the rock directly, without the suit's protection, would result in instant severe burns, the heat transferring rapidly to any cooler object in contact. But through the suit's insulation, the rock temperature remains a distant fact rather than a felt reality. The rocks also conduct the planet's internal heat to the surface, though the heat flow from Venus's interior is much less than the heat trapped by the greenhouse effect. Measurements from Soviet landers suggested heat flow values similar to Earth's average continental heat flow, around 60 to 70 milliwatts per square meter, indicating that Venus's interior cools at a rate similar to Earth's despite the lack of plate tectonics. This heat flow represents the slow leakage of primordial heat from the planet's formation, plus heat generated by radioactive decay of elements like uranium, thorium, and potassium in the mantle and crust. The heat eventually reaches the surface and radiates into the atmosphere. But at these flow rates, the contribution to surface temperature is negligible compared to the greenhouse heating. The lack of water in the rocks and regolith represents one of the most significant differences from Earth's surface materials. Where minerals commonly contain water molecules bound into their crystal structures, and where clay minerals formed by water weathering cover much of the land surface, Venus's rocks, formed in a dry environment and weathered without water, contain only trace amounts of water, if any, with most minerals being anhydrous varieties that form at high temperatures in water-poor conditions. The absence of clays and other hydrated minerals means the regolith behaves differently than Earth soil, lacking the cohesion that clay particles provide, and possibly being more friable and dusty, despite the atmospheric pressure preventing dust from dispersing widely. The surface here shows no signs of biological activity, no organic matter, no fossils, nothing that suggests life ever existed on Venus or exists here now. The high temperatures destroy organic molecules rapidly, and the sulfuric acid in the atmosphere would attack organic compounds, even if temperatures were lower. The sterility is absolute, The rocks and regolith completely inorganic, formed through geological processes alone, without the influence of biology that so shapes Earth's surface through soil formation, carbon cycling, and the deposition of organic-rich sediments. This lifelessness creates a strange purity, the landscape representing geology in isolation from the complexities that life introduces. The preservation potential for surface features on Venus differs dramatically from Earth due to the absence of water erosion and the limited wind erosion at the surface. On Earth, mountains erode away over tens of millions of years. Rivers carve valleys, glaciers scour landscapes, and coastlines constantly change. But on Venus, these water-driven processes do not occur. Wind erosion happens extremely slowly due to the dense atmosphere creating low wind speeds at the surface. So surface features can persist for hundreds of millions of years, or even billions of years, if protected from volcanic burial. This preservation creates a landscape where ancient features coexist with more recent features. Time compressed into the visible surface in ways different from Earth's constantly changing landscapes. The impact craters scattered across Venus preserve themselves similarly, their rims and ejecta blankets persisting largely unmodified since the impacts occurred. The craters range from a few kilometers to over 200 kilometers in diameter, with the largest crater, Meade, measuring about 270 kilometers across and displaying a prominent central ring structure. The craters provide age constraints for surface units, with heavily cratered regions being older and lightly cratered regions being younger. Though the overall low crater density compared to the Moon or Mars indicates most of Venus's visible surface is relatively young geologically. The absence of craters smaller than about 2 kilometers in diameter results from the thick atmosphere breaking up smaller impactors before they reach the surface, filtering out the smallest projectiles and leaving only the largest ones to create craters. Some rocks in the regolith might themselves be impact ejecta, material thrown out when a meteorite struck the surface elsewhere and created a crater, the excavated material flying through the atmosphere and landing here kilometers or even hundreds of kilometers from the impact site. These ejecta blocks would be difficult to distinguish from local volcanic rocks without detailed chemical or mineralogical analysis, but they represent another process that shapes the surface and distributes material across the landscape. The impacts also create shock metamorphosed rocks, material altered by the tremendous pressures of impact that can transform minerals into high-pressure forms, or melt rock completely. And some rocks in the regolith might show such shock features if examined closely enough. The ground's firmness and stability make it suitable for construction. Were anyone ever to attempt building structures on Venus, as the consolidated regolith and solid bedrock beneath provide foundations stronger than many Earth soils. The lack of groundwater and the absence of freeze-thaw cycles remove two major challenges that engineers face on Earth, though the extreme temperature and corrosive atmosphere create other challenges that would require entirely new materials and construction approaches. The Soviet Venera landers survived on this surface for periods ranging from 23 minutes to 127 minutes before succumbing to the heat and pressure, demonstrating that engineered objects can rest on Venus's surface, at least temporarily, before failing. The minerals composing these rocks remain stable at Venus surface conditions, with pyroxene, plagioclase, and olivine all having melting points well above the surface temperature. and being resistant to thermal breakdown. Some minerals undergo phase transitions or dehydration at lower temperatures, which is why hydrated minerals like clays cannot persist on Venus's surface. But the anhydrous silicate minerals that compose basalt remain solid and stable. This mineral stability means the rocks change very slowly once formed, with alteration occurring primarily through chemical weathering at the surface, rather than through thermal breakdown in the bulk of the rock. Walking across this rocky surface, the boots find purchase easily, despite the fine regolith covering, as the particles compact under pressure and the gravity, about 90% of Earth's surface gravity, provides sufficient weight for stable footing. The compaction of the regolith under pressure relates to Venus's surface pressure being 90 times Earth's atmospheric pressure, meaning the regolith particles are already experiencing significant compressive forces from the atmosphere above. Though this atmospheric pressure acts equally in all directions and doesn't create the same directional compaction that weight creates, the combination of gravity pulling downward and atmospheric pressure pressing from all directions creates a unique mechanical environment for the regolith different from either airless bodies or Earth. The rocks and regolith together create the tangible surface that defines Venus as a solid world rather than a gas giant, the boundary between the solid planet and the fluid atmosphere. The interface where geological processes meet atmospheric processes. This interface represents the accessible part of Venus, the portion that landers can touch and analyze, that rovers could traverse if built to withstand the conditions, that samples could someday be collected from and returned to Earth for detailed laboratory analysis. The surface holds the evidence of Venus's history, written in rock and landform, and understanding the composition and origin of these materials provides keys to understanding how Venus evolved from a planet, perhaps similar to early Earth, into the scorched world it is today. Standing here on this foundation, surrounded by ancient basalt and weathered regolith, the ground represents both an endpoint and a beginning. The current surface that results from billions of years of planetary evolution and the starting point for understanding the processes that created it. Each rock contributes a small piece of evidence. Each mineral grain records a moment of crystallization from molten rock, and together they tell the story of Venus's volcanic past and its ongoing geological present. And while the ground provides the foundation for this exploration, the landscape extends beyond this immediate spot, and moving across the surface toward different terrain will reveal how Venus's geology varies from place to place, and how the processes that shaped this world created the diversity visible in orbital images. The decision to move comes after thoroughly understanding the immediate surroundings. After the rocks and regolith and nearby landforms have become familiar enough, the curiosity turns toward what lies beyond the visible horizon. Movement across Venus requires preparation and planning, as the environment resists casual travel, and each kilometer traversed demands energy and time. The thick atmosphere pushes back against any motion through it, creating drag forces far greater than air resistance on Earth, making even slow movement feel like wading through water rather than walking through air. The suit compensates for this resistance, its powered joints and servos providing the force needed to move limbs and maintain balance against the atmospheric pressure. Without this assistance, simply walking would require enormous effort, as moving an arm or leg through 90 Earth atmospheres of dense carbon dioxide creates resistance comparable to moving through molasses. The suit's systems manage this resistance automatically, sensing the wearer's intended movements through pressure sensors and position tracking, then applying exactly enough force through the powered joints to make the movement feel natural despite the hostile environment outside. The mechanical systems hum quietly with each movement, the sound transmitted through the suit's structure, but barely audible over the suit's life support fans and pumps. The pace of travel remains slow by necessity, perhaps 1 or 2 kilometers per hour at most, with frequent pauses to rest and to observe the changing landscape. Moving faster would tax the suit's power systems and cooling systems too heavily, as the work of pushing through the atmosphere generates heat that must be removed to prevent the suit's interior from overheating. The cooling system circulates chilled fluid through channels in the suit's inner layers, absorbing body heat and mechanical heat, then transferring this heat to a radiator system that somehow manages to reject heat even in an environment that is itself at 900 degrees Fahrenheit. The engineering required to make such cooling possible represents technology beyond current capabilities, part of the thought experiment that allows this journey to occur. The direction of travel becomes important when no landmarks provide obvious destinations and when navigation cannot rely on the sun's position due to the clouds hiding it. The suit's navigation systems track position through inertial measurement, using accelerometers and gyroscopes to detect every movement and calculate current position relative to the landing site. This dead reckoning approach accumulates errors over time, but for journeys of a few dozen kilometers over a few days, the errors remain small enough for practical navigation. The system displays a simple map showing the landing site, the current position, and any waypoints marked for future reference, providing orientation in a landscape where every direction looks similar. The first steps away from the landing site create a mixture of feelings, the security of the familiar spot giving way to the uncertainty of unknown terrain. Yet the landscape ahead calls with the promise of new observations and new understanding. The boots press into the regolith with each step, leaving footprints that will likely persist for millions of years in this waterless, nearly windless environment, creating a permanent record of this journey. Looking back shows the trail of footprints leading back toward the landing site, the marks clearly visible in the fine surface material. Each print showing the tread pattern of the boot sole with remarkable clarity. The horizon distance on Venus, about 3 kilometers from a standing height of 2 meters, means the landing site remains visible for some time as travel begins. But eventually, distance and atmospheric haze obscure it, and the landmark disappears into the orange murk. The psychological effect of losing sight of the landing site creates a moment of isolation, of being truly alone in the Venusian landscape with no visible reference to human presence. Only the suit and the endless rocky plain. The isolation feels profound, yet strangely peaceful. The absolute stillness of the environment and the unchanging orange glow creating a contemplative atmosphere, conducive to slow, careful observation. The landscape changes gradually as the trek continues, the volcanic plain showing subtle variations in surface texture and rock distribution. Some areas show more regolith coverage with fewer exposed rocks, creating smoother surfaces, while other areas expose more bedrock or larger boulders, creating rougher terrain. The variations likely reflect different lava flow episodes, with some flows having produced rockier surfaces, and others having produced smoother surfaces, depending on the lava's viscosity, eruption rate, and cooling rate. The boundaries between different flow units sometimes show as subtle changes in color or texture. The transition's gradual rather than sharp, marking where one flow overlapped or abutted another. Small craters appear occasionally, typically a few meters to a few tens of meters in diameter, their rims slightly elevated above the surrounding plain, and their interiors filled with regolith that has gradually accumulated since the impacts occurred. These small craters represent secondary impacts, created not by meteorites from space, but by debris thrown out when larger impacts occurred elsewhere. The ejected material falling back to the surface at high speed and creating its own smaller craters. The secondary craters cluster around larger primary craters, creating patterns visible in orbital images. But from the surface, the pattern is difficult to discern, and each crater appears as an isolated feature without obvious connection to others. The walking rhythm develops into a steady cadence, step after step, each movement deliberate and controlled, the landscape slowly sliding past to either side as forward progress accumulates. The experience resembles a very slow hike, the pace meditative, the surroundings demanding attention to avoid obstacles, yet repetitive enough that the mind can wander while still maintaining awareness. The suit's systems maintain their steady operation, the life support continuing without interruption, the cooling system preventing overheating, the structural integrity holding back the crushing pressure, all these functions continuing automatically while attention focuses on navigation and observation. The regolith underfoot shows patterns in places, subtle lineations or textures that might indicate wind action, though the surface winds are generally too gentle to move particles significantly. Alternatively, the patterns might result from the way material settled after being disturbed by impacts, or from compression under the atmospheric pressure, creating organized structures in the loose material. Reading the patterns requires knowledge of sedimentary processes and how particles arrange themselves under different conditions. Knowledge that helps interpret what the surface textures reveal about the forces acting on them. The occasional larger rock breaks the monotony of the walk. Boulders ranging from basketball-sized up to car-sized resting on the surface. Their origins either as ejecta from distant impacts or as fragments from bedrock outcrops that have broken apart through thermal stress or chemical weathering. Approaching one of the larger boulders provides opportunity to examine volcanic rock in more detail, seeing the vesicles, the mineral crystals, the weathered rind more clearly than possible with smaller samples. The boulder provides a landmark, a recognizable feature that could serve as a waypoint for return navigation. Though in this largely featureless plain, such landmarks are precious and rare. Resting against the boulder, the suit's weight, supported by the rock's mass, provides a moment to survey the surroundings and appreciate the distance covered. Looking back shows the trail of footprints extending toward the now invisible landing site, while looking forward shows more of the same terrain extending to the hazy horizon. The sameness could become monotonous, but instead it creates a meditative quality, the lack of dramatic scenery, paradoxically making small variations more noticeable and more interesting. A slight change in rock density, a barely perceptible slope, a subtle color variation in the regolith, all become noteworthy in a landscape where dramatic features are absent. The trek continues from the boulder, the rhythm re-establishing, the distance gradually increasing. Navigation becomes more important as distance from the landing site grows, as getting lost in this environment would be serious despite the suit's capabilities, since power reserves and life support consumables limit the total time available for this journey. The suit provides several days of autonomy, but wandering aimlessly would waste that time without advancing the exploration goals. So maintaining awareness of position and direction remains essential, even when every direction looks similar. The changing angle of weak sunlight becomes noticeable over many hours, though the diffuse glow makes precise sun position difficult to determine. The subtle shift from one general direction of slightly greater brightness to another marks the passage of time as Venus rotates, the day creeping forward at its glacial pace. A full Venusian day requires 243 Earth days to complete one rotation, meaning the sun's apparent position in the sky changes extremely slowly, barely perceptible over the hours of this trek, but measurable over the full day. The temperature remains constant during the walk, the surface heat neither increasing nor decreasing with the subtle changes in illumination, as the massive atmosphere absorbs and redistributes heat so effectively that day-night temperature variations at the surface remain minimal. The suit's external temperature sensors show readings steady within a few degrees across hours of travel. The thermal stability remarkable compared to Earth's surface, where temperature can vary significantly between day and night, or between sun and shade. This thermal constancy results from the greenhouse effect and the thick atmosphere working together to maintain surface conditions that vary little with time or location, at least at similar elevations. The distant horizon occasionally shows features that might be topographic variations, subtle darkening or lightening that could indicate rising or falling terrain, though atmospheric haze makes interpretation uncertain. These possible features become targets for the next phase of exploration, goals that provide direction and purpose to the continued trek. Moving towards slightly elevated ground would provide better views of the surrounding terrain and might reveal different geological features than the plains, making the effort of reaching such areas worthwhile, despite the energy expenditure required. The psychological aspect of the trek occupies as much attention as the physical, as the isolation and strangeness create mental states different from any terrestrial hiking experience. The absolute certainty of hostility outside the suit creates a background awareness of danger, despite the suit's reliable protection. A reminder that this environment allows no mistakes, no equipment failures, no careless moments. Yet this awareness does not create fear, but rather heightened appreciation for the suit's capabilities, and for the opportunity to experience a world no human has actually walked upon, a landscape known only through spacecraft images and lander data, until this imagined journey made it tangible. The beauty of the landscape reveals itself slowly, not through dramatic vistas, but through subtle qualities, the play of orange light on rock surfaces, the textures of the regolith, the ancient stillness of a world untouched by weather or life. The harshness and the beauty coexist, neither diminishing the other, both aspects of Venus's reality. The trek becomes a moving meditation, each step a small achievement, the accumulating distance a gradual revelation of this world's character and diversity. And ahead, slowly emerging from the haze as the trek continues, the land begins to rise. The slope starts so gradually that at first it barely registers as different from the flat plains. Just a slight increase in the effort required for each step forward, a subtle sense of climbing rather than walking level. The incline remains gentle, perhaps only a few degrees, but sustained over many kilometers, it represents significant elevation gain, hundreds of meters of vertical rise from the plains below toward the highland regions that form Venus's elevated terrain. These highlands cover about 10% of Venus's surface, rising above the mean planetary radius and creating the only major topographic relief on a world otherwise dominated by flat volcanic plains. The transition from plains to highlands marks a geological boundary, moving from the younger volcanic resurfacing units that cover most of the planet toward older, more complex terrain that might have survived the most recent major volcanic episodes. The highland regions show different characteristics in orbital radar images, with more complex surface textures and evidence of tectonic deformation that suggests different geological processes operated here compared to the plains. Understanding these differences requires reaching elevated terrain and examining it directly, seeing what rocks and structures exist here that distinguish highlands from lowlands. The effort of climbing grows more noticeable as the slope continues, the suit's servos working harder to lift the combined weight of suit and wearer against Venus's gravity. The power consumption increases slightly, the battery reserves depleting faster during climbing than during level walking, creating awareness of energy budgets and the need to balance exploration ambitions against power limitations. The suit's display shows remaining battery capacity and estimates how many hours of operation remain at current consumption rates, information that helps plan how far to climb and when to stop and rest. Rest periods become more frequent as the climb progresses, stops to catch breath and to allow the suit's cooling system to dissipate the accumulated heat from exertion and mechanical work. During these pauses, turning to look back reveals the volcanic plains spreading below, the view expanding as elevation increases and the horizon distance grows. From a few hundred meters above the plains, the horizon extends perhaps 4 or 5 kilometers instead of 3, the extra distance revealing more of the landscape's character and showing features invisible from the lower elevation. The rocks along the slope show similar composition to the plain's basalts, but the terrain becomes rougher and more broken, with exposed bedrock outcrops appearing where regolith cover thins on the steeper slopes. These outcrops provide opportunities to see the structure of the lava flows more clearly, revealing how individual flows stack atop one another, each flow representing a separate volcanic episode. The flow boundaries appear as subtle changes in vesicle density or grain size, marking where one flow surface was buried by the next eruption. The contacts preserved in the rock record, like pages in a book detailing volcanic history. The highland regions ahead, still distant but becoming more clearly visible as elevation increases, show different radar properties in the orbital images, appearing brighter in some radar wavelengths than the plains. This brightness difference suggests differences in surface roughness or composition, with some scientists interpreting the radar signatures as indicating the possible presence of minerals that form at higher elevations, where temperatures might be slightly cooler. Minerals that would weather differently than the basalts dominating lower elevations. These interpretations remain uncertain, without direct sampling, but they create expectations about what might be found upon reaching the highland proper. After several hours of climbing, the slope levels onto a plateau, a relatively flat area at elevated position above the plains, creating a natural stopping point to rest and observe before continuing higher. The plateau surface shows rocky terrain with less regolith cover than the plains below. The exposure of bedrock creating rougher surfaces that might result from either less weathering at this elevation or from the slope being too steep for regolith to accumulate as thickly as it does on flatter ground. Walking across the plateau requires more careful attention to footing, as stepping on unstable rocks could lead to falls. And while Venus's lower gravity makes falls less dangerous than on Earth, the suit's bulk and the atmospheric resistance make getting up again awkward and energy-intensive. The view from the plateau provides perspective on the journey so far. The trail of footprints visible at intervals where the slope's angle allows seeing back down the path climbed. The landing site lies somewhere beyond the horizon now. Invisible from this elevation, the distance covered, measuring several kilometers of horizontal distance, plus several hundred meters of vertical rise. The accomplishment feels modest in absolute terms, but significant in context, as few spacecraft have visited Venus, and none have moved across its surface like this imagined journey allows. Ahead, the terrain rises again toward the true highland regions, where Tessera terrain creates the complex ridged and grooved surfaces that distinguish Venus's oldest visible crustal material from the younger plains. Tessera terrain covers about 8% of Venus's surface, concentrated in the highland regions, and shows evidence of multiple episodes of deformation that folded and fractured the crust before volcanic plains buried the margins. Reaching Tessera terrain becomes the goal for the remainder of the climb, as seeing this complex geological province directly would reveal details invisible in orbital data. The climb continues from the plateau, the slope steepening in places, creating challenges for navigation and requiring sometimes contouring around obstacles rather than climbing directly. The route becomes less straight, following the path of least resistance upward, switchbacking across slopes too steep for direct ascent. The slower progress suits the contemplative pace, creating time to observe the rock formations and landscape features encountered along the way, treating the journey itself as valuable as the destination. The temperature sensors show a slight decrease as elevation increases, dropping from about 475 degrees Celsius at the plains to perhaps 465 or 470 at several hundred meters elevation. The pressure also decreases slightly, though still measuring above 85 atmospheres. The reduction barely noticeable compared to the crushing weight of pressure at lower elevations. These variations with altitude follow predictable atmospheric physics, with both temperature and pressure decreasing as distance from the surface increases, though the gradients remain much gentler than on Earth due to Venus's much thicker atmosphere creating more gradual changes. The rocks here occasionally show mineral crystals large enough to identify visually, possibly plagioclase or pyroxene crystals that grew to centimeter scale during slow cooling of thick lava flows. These larger crystals catch the orange light differently than the fine-grained matrix surrounding them, creating subtle sparkles or reflections that draw the eye. Collecting samples, if such were possible, would allow detailed mineralogical analysis that could reveal temperatures and pressures of formation, magma compositions, and cooling histories. Information that builds understanding of volcanic processes and planetary evolution. The highland terrain ahead shows in the improving view the complex surface topography creating patterns of light and shadow, even in the diffuse Venusian illumination. The ridges and troughs of Tessera terrain create a texture visible from kilometers away, the surface appearing wrinkled or creased, like fabric that has been compressed and folded. This appearance reflects the reality of Tessera formation, where tectonic forces compressed and extended the crust multiple times, creating the complex patterns of intersecting ridges and troughs that characterize this terrain type. Reaching the edge of Tessera terrain creates a sense of arrival, of having climbed from the ordinary plains to something geologically special and rare. The boundary between smooth plains and complex Tessera appears as a gradual transition over hundreds of meters, the ridges beginning as subtle undulations in the plains and growing more pronounced upward until they dominate the landscape completely. The scale of the deformation becomes apparent upon reaching the Tessera proper, with ridges rising tens to hundreds of meters above intervening troughs, creating topography that requires navigating around or over rather than simply walking across. The Tessera ridges show layering in places, suggesting multiple deformation episodes created the complex structure through successive compression and extension events. Some ridges trend roughly east-west, while others trend north-south, the intersecting patterns creating a grid-like appearance in orbital images that from the ground appears as chaotic, jumbled terrain. Walking among the ridges creates perspective on the scale, the human figure dwarfed by landforms that extend for kilometers, each ridge representing enormous forces acting on the crust over geological time. The rocks composing the Tessera show similar basaltic composition to the plains, suggesting the deformation affected volcanic rocks rather than some different crustal material. Though some scientists have proposed Tessera might represent a different rock type, possibly more similar to granite or andesite. Determining the exact composition would require detailed chemical analysis beyond what visual inspection provides, but the weathering patterns and general appearance suggest continuity with the plains basalts rather than dramatically different composition, implying the Tessera's unique character comes from deformation history rather than from different starting materials. The view from among the Tessera ridges shows the volcanic plains far below and beyond, the highlands standing as islands of complex terrain amid the smoother lava-flooded lowlands. The perspective creates appreciation for Venus's geological diversity, the planet revealing itself as more varied than the simple volcanic plains description suggests, with highlands, Tessera terrain, volcanic features, impact craters, and complex structures creating a rich geological tapestry. The week available for exploration allows sampling this diversity, visiting different terrains, seeing how Venus's geological processes created landscapes that vary from place to place, despite the uniform crushing heat and pressure. And while Tessera terrain represents ancient deformation, volcanic features represent the processes that resurfaced most of the planet more recently. And seeing such features directly means continuing the journey toward regions where volcanic mountains rise above even these elevated highlands. The volcanic features visible in orbital radar images dominate Venus's geological landscape, creating mountains and calderas and complex structures that reveal the planet's internal heat and magmatic activity. Finding such features requires knowing where to look, as the highlands contain volcanic mountains amid the Tessera terrain, shield volcanoes, and other structures that rise above the already elevated ground. The trek towards such features begins from the Tessera region, moving across complex terrain toward areas where orbital data indicates major volcanic edifices exist. The first volcanic feature encountered appears as a gradual swelling of the ground, a broad dome rising perhaps a kilometer above the surrounding Tessera terrain, over a horizontal distance of many tens of kilometers. This gentle slope characterizes shield volcanoes, mountains built from countless eruptions of low-viscosity lava that flowed easily and spread across wide areas before solidifying. The slope is so gentle that walking up it barely feels like climbing, the incline perhaps only 2 to 5 degrees, yet sustained over enough distance to create mountains rivaling Earth's largest volcanoes in volume. Moving up the flank of the shield volcano, the surface shows lava flow structures more clearly than in the plains, with flow fronts visible where lava advanced and froze, creating step-like features a few meters high. The flows overlap one another in complex patterns, showing how the volcano grew through many separate eruptions rather than a single massive event, each flow adding another layer to the growing mountain. The flow surfaces show ropey or folded textures in places, patterns frozen into the rock when the surface of the flow solidified, while liquid lava continued moving beneath, creating folds and wrinkles similar to those seen in Hawaiian lava flows. The vesicles in the volcanic rocks here appear more abundant than in the plains basalts, possibly because volcanic gases came out of solution more readily from lavas erupting at the summit of a growing mountain, where atmospheric pressure was lower than at the plains below. The higher vesicle density gives some rocks an almost spongy appearance, the holes so abundant that the remaining rock forms thin walls between adjacent vesicles, creating fragile structures that break easily when handled. These highly vesicular rocks might represent the uppermost parts of lava flows where gas concentration was highest, or they might represent volcanic spatter thrown out during more vigorous eruptive phases. Approaching the summit caldera requires several hours of steady climbing, the distance from base to summit covering dozens of kilometers, despite the gentle slope. The summit itself reaches perhaps 2 to 3 kilometers above the surrounding plains, though from the volcano's flank, the summit remains invisible beyond the horizon, revealing itself only as the climb progresses and elevation increases. The atmospheric haze continues to limit visibility, but the expanding horizon with altitude means more of the planet comes into view from higher elevations. The caldera appears first as a flattening of the slope, and then as the ground beginning to drop away, the rim marking where the summit once stood before the chamber beneath emptied and the overlying rock collapsed into the void. Approaching the rim with appropriate caution, as the stability of caldera walls can be uncertain, reveals the interior stretching away downward and across. A depression several kilometers in diameter and hundreds of meters deep. The floor of the caldera appears relatively flat, possibly filled by late-stage lava that ponded in the depression after the main collapse occurred, or possibly flattened by collapsed debris that accumulated and settled over time. The walls of the caldera show layering clearly, revealing the stacked lava flows that built the volcano before the summit collapsed. Each layer represents a separate eruptive episode, the stratigraphy recording the volcano's construction from base to summit, the sequence reading from bottom to top as a chronicle of volcanic history. Some layers appear thicker than others, indicating more voluminous eruptions, while thinner layers represent smaller eruptions that added less material. The total number of layers visible in the caldera walls suggests hundreds or thousands of individual eruptions occurred to build this volcano to its current size. Standing at the caldera rim creates a moment of perspective. Looking down into the collapsed structure and seeing the vertical exposure of the volcano's interior. A cross-section usually hidden beneath the outer slopes. The depth creates a sense of scale, hundreds of meters of vertical relief, from rim to floor. The walls steep enough in places to appear nearly vertical, though gravitational stability would prevent truly vertical walls from forming without structural support. The orange light, filtering into the caldera, creates a glow on the far wall, while the near wall falls into shadow. The diffuse illumination still creating subtle lighting variations, despite the lack of sharp shadows. The floor of the caldera, visible far below, shows no signs of current activity, no glow from molten lava, no emissions of gas, no evidence that this volcano remains active. The question of whether Venus's volcanoes currently erupt remains debated, with some evidence suggesting recent activity, but without definitive proof of eruptions happening within the last few years. This particular volcano likely last erupted hundreds of millions of years ago, based on the statistical age estimates from crater counting, though individual volcanoes might be much younger or older than the surface average. Moving around the caldera rim provides different perspectives on the interior structure and the surrounding landscape. From the summit, the view extends to the horizon in all directions. The volcanic plains spread below like an orange-grey sea. Other volcanic features, visible as distant rises, or as brighter or darker patches where different lava flows create variations in radar reflectivity. The Tessera terrain appears as rougher ground surrounding the volcano, while smooth plains extend beyond toward the horizon. The landscape revealing its large-scale structure from this elevated vantage point. Other volcanic features visible from the summit include what appear to be volcanic domes in the distance, probably pancake domes based on their circular shape, and apparent flat tops visible in the hazy distance. These features represent different volcanic processes, their formation requiring more viscous lava that could not flow far from the vent, and instead piled up near the source, creating steep-sided structures rather than gently sloped shields. Visiting such features would reveal different volcanic morphologies and possibly different rock compositions, but the distance makes reaching them during this journey impractical given time and power constraints. The summit area shows fractures radiating from the caldera, cracks where the ground broke under stresses related to the summit collapse or to magma movement beneath. Some fractures extend hundreds of meters away from the rim, their widths ranging from centimeters to meters, their depths difficult to determine without careful examination. Walking across fractured ground requires attention to avoid stepping into cracks hidden by regolith or by shadows. Though most fractures announce themselves clearly as breaks in the otherwise continuous surface, the presence of these fractures indicates tectonic stresses acted on the summit region, possibly from magma chamber inflation and deflation cycles during the volcano's active period, or from regional tectonic forces unrelated to volcanic processes. Reading stress indicators from fracture patterns requires geological expertise, but the general pattern of radial fractures around a caldera suggests the collapse itself created most of the breaking through, slumping of material into the depression. Additional fractures might record earlier stresses from when magma rose through the crust to feed eruptions at the surface. Descending from the summit toward the volcano's flank provides opportunity to examine the downslope surface in more detail, seeing how individual lava flows stacked and overlapped to build the edifice. Some flows show channels where lava concentrated into rivers during eruption, the channels cutting several meters into the flow surface and creating conduits that carried molten rock downslope. The channels sometimes show levees, raised banks on either side created when lava splashing against the channel walls built up ridges of solidified material. These features, exactly analogous to similar structures in Hawaiian and Icelandic lava flows. The diversity of flow morphologies creates visual interest, despite all the rocks being compositionally similar basalts, as the different eruption conditions, flow rates, temperatures, and cooling rates created different textures and structures. Some flows are smooth and ropey, others are rough and blocky. Some show channels, and others show broad, sheet-like forms. The variety recording different moments in the volcano's history when conditions differed slightly. This frozen record of variation demonstrates that even though Venus's surface appears monotonous at large scale, closer examination reveals details that distinguish one area from another and one volcanic event from another. The descent continues down the volcano's flank, retracing the climb in reverse, the caldera eventually disappearing beyond the backward horizon as distance increases. The Tessera terrain reappears ahead, the complex ridged ground awaiting the return journey. The volcano has revealed its structure and history through direct observation, adding understanding about Venusian volcanism that complements but goes beyond what orbital data provides. The scale, the structure, the caldera morphology all become real through walking among them rather than remaining abstract interpretations of radar images. And while volcanic mountains reveal one aspect of Venus's geology, the way light and illumination work on this planet represents another dimension of understanding, one that affects every observation and creates the unique visual character of the Venusian surface environment. The quality of light on Venus shapes every visual experience, creating an environment unlike anywhere on Earth and fundamentally different from the harsh, direct sunlight on airless worlds like the Moon. Understanding how illumination works here requires examining the path that sunlight takes from the sun through the thick atmosphere to the surface, and understanding why the result creates such distinctive and unusual lighting conditions. The light that reaches the surface has traveled through more than 50 kilometers of dense carbon dioxide atmosphere and multiple layers of sulfuric acid clouds, undergoing scattering and absorption that transforms it completely from the white sunlight that left the sun 8 minutes earlier. The clouds begin about 48 kilometers above the surface, where temperatures drop low enough that sulfuric acid vapor condenses into tiny droplets that form the main cloud deck. These clouds extend upward to about 70 kilometers altitude, creating a layer more than 20 kilometers thick, composed entirely of sulfuric acid aerosol particles, ranging from less than 1 micron to several microns in diameter. Sunlight entering this cloud layer scatters from droplet to droplet, bouncing through the clouds in random directions, with some light reflecting back to space, and some gradually working its way downward toward the surface. The cloud layer reflects about 75% of incoming sunlight back to space, making Venus one of the brightest objects in Earth's sky. But the remaining 25% penetrates deeper. Below the main cloud deck, a haze layer extends from about 48 kilometers down to about 30 kilometers, containing smaller sulfuric acid particles and probably some dust particles, creating a transition zone between the dense clouds above and the clearer atmosphere below. This haze continues the scattering process, diffusing the light further so that by the time it reaches the lower atmosphere, it carries no directional information about where the sun sits in the sky. From about 30 kilometers down to the surface, the atmosphere remains relatively clear of particles, but the sheer density of carbon dioxide molecules creates Rayleigh scattering, the same process that makes Earth's sky blue. Except on Venus, the scattering follows different rules due to carbon dioxide's optical properties. The color transformation from white sunlight to orange surface illumination occurs primarily through two mechanisms working together. The sulfuric acid clouds scatter blue and green wavelengths more efficiently than red and orange wavelengths, preferentially removing shorter wavelengths from the downward traveling light and allowing longer wavelengths to penetrate more easily. Meanwhile, the dense carbon dioxide atmosphere near the surface absorbs some blue light and scatters remaining light multiple times, creating the characteristic orange glow that dominates the visual spectrum at ground level. The result is illumination shifted strongly toward the red-orange end of the spectrum, with very little blue or green component remaining by the time the light reaches the surface. The brightness level at the surface, despite the heavy filtering by clouds and atmosphere, remains surprisingly high, comparable to an overcast day on Earth, providing enough illumination for color photography and detailed visual observation. Measurements from Soviet Venera landers quantified surface illumination at between 1,000 and 3,000 lux, depending on solar angle and cloud thickness, compared to about 10,000 to 25,000 lux on an overcast Earth day, and about 100,000 lux in full Earth sunlight. This relatively high surface brightness, despite 95% of sunlight being either reflected to space or absorbed in the atmosphere, results from the scattering properties of the clouds and atmosphere efficiently channeling the remaining 5% down to the surface, rather than absorbing it entirely. The diffuse nature of surface illumination means light arrives from all directions simultaneously rather than primarily from one direction, as happens under direct sunlight on Earth. Looking upward shows the entire sky glowing with relatively uniform brightness, perhaps slightly brighter in the general direction of the sun, but without any clearly defined brighter region or solar disk visible through the haze. This omnidirectional illumination creates the soft, shadowless lighting that characterizes the Venusian surface, as every point on the ground receives light from essentially the entire hemisphere of sky above it, preventing the formation of shadows that require directional light sources. The absence of sharp shadows affects depth perception and spatial awareness in subtle ways, as human visual systems rely partly on shadow information to judge distances and surface contours. On Venus, these depth cues diminish, making the landscape appear flatter and less three-dimensional than it actually is. requiring more careful attention to other depth indicators, like texture gradients and relative sizes. Rocky surfaces show their roughness through texture rather than through shadow patterns, with slight variations in color and grain size, providing information that shadow details would normally contribute. The adaptation to this lighting takes conscious effort initially, but becomes natural with extended exposure as the visual system learns to extract information from available cues. Photography in Venusian lighting requires different approaches than terrestrial photography, as the uniform illumination eliminates harsh shadows but also reduces contrast and visual drama. Colors appear shifted toward orange across the entire scene, requiring either acceptance of the orange cast as authentic Venus color or post-processing correction to show what materials would look like under white light. Exposure settings remain relatively straightforward due to the even lighting, with no bright highlights or deep shadows creating extreme dynamic range that challenges camera sensors. The scene existing entirely in mid-tones without strong brightness variations. The suit's external cameras capture images continuously during the journey, recording both still images and video that documents the landscape and observations. These images show the orange lighting clearly, rocks and regolith rendered in shades of orange-grey, the sky a deeper orange, fading to brown near the horizon, where atmospheric path length increases. Processing these images to remove the color cast reveals the actual rock colors, mostly grey basalts with occasional brown weathering products. But the orange versions represent the authentic appearance as actually experienced at the surface. Both versions provide value, the orange images showing true appearance, while the color-corrected images reveal material properties independent of illumination. The suit's helmet visor filters and conditions the incoming light to optimize visibility while protecting the eyes from any harmful wavelengths. Though at surface level, harmful ultraviolet radiation has been completely absorbed by the atmosphere above and poses no threat. The visor might enhance contrast slightly to compensate for the flat lighting, or might adjust color balance to provide more natural appearing colors while maintaining enough orange cast to preserve the sense of place. The exact image processing happens automatically and transparently, creating a view that feels natural and unprocessed, even though technically the raw light has been modified for optimal perception. Observing how light interacts with different surface materials reveals subtle variations in reflectivity and color that indicate compositional or textural differences. Some rocks appear slightly lighter or darker than others, variations that might indicate different mineral content, different weathering states, or different grain sizes affecting how much light the surface absorbs versus reflects. The regolith shows subtle color banding in places, probably from deposition of material from different sources, each band reflecting light slightly differently and creating stripes or patches visible in the uniform illumination. These variations would be much more dramatic under white light, but even in orange illumination, they provide information about surface properties and processes. The horizon distance, limited to about 3 kilometers from standing height at plains level and extending to 4 or 5 kilometers from elevated positions, results partly from Venus's curvature and partly from atmospheric haze that obscures distant features even when they lie above the geometric horizon. The scattering that creates the diffuse illumination also creates a distance haze, where multiple scattering events blur distant objects and reduce contrast until they fade into the background glow. Features beyond about 5 kilometers distance become difficult to distinguish even from elevated vantage points, creating a sense of limited visibility despite the relatively bright illumination. This restricted visibility affects navigation and exploration strategy, as distant landmarks remain invisible until approached within a few kilometers, preventing the long-distance route planning possible in clear Earth atmospheres or in airless environments where horizons extend much farther. The exploration becomes more local and immediate, focused on what lies within visible range, with longer-range planning dependent on maps derived from orbital radar data rather than visual reconnaissance. The trade-off between the interesting diffuse lighting and the limited visibility represents one of many ways Venus's environment creates both advantages and challenges for surface exploration. The light levels change gradually as the Venusian day progresses, though the changes occur so slowly given the 243-day rotation period that detecting them requires many hours of observation. Over a full day, the region directly under the Sun sweeps westward very slowly as Venus rotates eastward in its retrograde motion, creating gradual shifts in which part of the sky shows slightly greater brightness. At any moment, the change is imperceptible. But comparing morning observations to evening observations, separated by Earth days, shows measurable differences in illumination angle and brightness distribution across the sky. The transition from day to night happens so gradually that pinpointing sunset as a specific moment becomes meaningless. Instead, the daylight dims imperceptibly over many hours as the sun's elevation angle decreases and more atmosphere lies between the sun and the surface. The increasing path length through the atmosphere reduces surface illumination slowly, the orange glow fading toward darker orange and eventually toward a dim brown that never becomes truly black. Even at local midnight, with the sun directly on the opposite side of the planet, some light scatters through the atmosphere from the sunlit side, preventing complete darkness and maintaining a perpetual deep twilight condition. Navigation by celestial objects, impossible even during the day due to cloud cover, remains equally impossible at night as the darkness and haze prevent seeing stars or other planets. The suit's navigation systems must rely entirely on inertial tracking and mapping, with no possibility of obtaining position fixes from astronomical observations. This limitation, shared with submarines operating underwater or aircraft flying through clouds, requires careful attention to navigation system accuracy and periodic calibration using known landmarks when visible, ensuring position estimates do not drift too far from reality. The psychological effect of the lighting, both the perpetual orange glow during day and the dim brownish twilight at night, creates an otherworldly atmosphere that reinforces the alienness of Venus while becoming familiar through continued exposure. The constancy of the color scheme, everything rendered in variations of orange and brown, creates a visual environment utterly unlike Earth's varied colors. Yet, the human visual system adapts and begins to distinguish subtle color variations within the narrow range available, seeing distinctions between different shades of orange that initially appeared uniform. And while the lighting remains relatively constant, the planet itself rotates slowly beneath the fixed clouds, creating the progression from day to night and back to day that defines one measure of time on this world, where days and years intertwine in unusual relationships. The rotation of Venus creates the rhythm of day and night that governs illumination patterns and establishes one fundamental timescale for planetary processes. Though this rotation proceeds so slowly that it defies human intuition about what day and night mean. Venus rotates retrograde, meaning it spins in the opposite direction from most planets, turning clockwise when viewed from above the North Pole, while Earth and most other planets spin counterclockwise. This backward rotation combines with the slow rotation rate to create unusual relationships between rotation period, orbital period, and the length of a solar day, from sunrise to sunrise. The rotation period, measured relative to the fixed stars, lasts 243.025 Earth days, making Venus the slowest rotating planet in the solar system. During this time, the planet completes slightly more than one orbit around the Sun, as Venus's orbital period lasts only 224.7 Earth days, creating the unusual situation where a Venusian day exceeds a Venusian year. The combination of retrograde rotation and the orbital motion creates a solar day, the time from sunrise to sunrise at a fixed location of 116.75 Earth days, meaning the sun rises in the west, takes 58 Earth days to cross the sky to the east, sets, and another 58 Earth days pass in darkness before the next sunrise. Standing on the surface, experiencing this rotation requires patience and time awareness, different from Earth's familiar 24-hour cycle, as perceptible changes in illumination occur over many hours rather than minutes, and significant changes, like sunrise or sunset, require waiting through what would be months on Earth. The week available for this journey allows experiencing only a small fraction of one Venusian day, perhaps enough time to notice slight changes in light direction and intensity, but not enough to witness a complete sunrise or sunset. The current exploration falls within the daytime period, with the sun somewhere above the horizon, though invisible through the clouds, maintaining the orange glow that marks Venusian daylight. The gradual dimming that marks the approach of night begins imperceptibly, the orange glow perhaps fractionally less bright over many hours. The change so slow that comparing current conditions to memory from hours ago shows more difference than moment-to-moment observation reveals. The suit's light meters quantify the changes that eyes barely detect, recording the slow decrease in illumination levels as the sun's elevation angle above the horizon drops, and the atmospheric path length through which sunlight must travel increases. The lengthening path through the atmosphere scatters and absorbs more light, reducing surface brightness proportionally to the added distance that sunlight crosses through dense gas. The temperature, which might be expected to drop as illumination fades, remains essentially constant due to the massive thermal inertia of the dense atmosphere and the greenhouse effect that traps heat near the surface. Measurements from Soviet landers show day-night temperature variations of only a few degrees at most, with some locations showing essentially no measurable change between noon and midnight. The atmosphere circulates heat globally through large-scale wind patterns, redistributing warmth from the day side to the night side, and from equatorial regions toward the poles, maintaining remarkably uniform temperature across the entire planetary surface. This thermal stability means the environment changes very little between day and night, with illumination being the primary variable rather than temperature. As darkness gradually deepens over many hours, the orange glow fades through darker shades, becoming brown, and eventually approaching something like deep twilight on Earth, though never reaching the complete blackness that nighttime achieves on Earth, away from artificial lights. The scattering of sunlight through the thick atmosphere ensures that some illumination persists, even when the sun sits well below the horizon, the light path extending around the planet's limb through the upper atmosphere and scattering downward to create a permanent glow. The darkest conditions, occurring at local midnight when the sun reaches its lowest point below the horizon, reduce illumination to perhaps 10 to 100 lux, similar to heavy twilight or a very dimly lit indoor space on Earth. The inability to see stars, even during the darkest night, represents one of the significant losses compared to nighttime on Earth, where stars, planets, and the moon provide celestial reference points and natural beauty. On Venus, the thick, hazy atmosphere prevents any celestial objects from appearing, creating a sky that remains featureless whether day or night, showing only variations in the intensity of its orange-brown glow. The isolation this creates feels profound, as if Venus exists cut off from the rest of the universe, surrounded by clouds that hide both the surface from space and space from the surface. The perpetual overcast creates a closed world focused inward on its own geology and atmosphere, rather than outward toward the cosmos. The psychological effect of darkness lasting weeks creates challenges for human circadian rhythms and mental well-being. As biological systems evolved under Earth's 24-hour day-night cycle struggle to adapt to the Venusian timescale, the suit compensates with interior lighting on an artificial day-night schedule, maintaining Earth-normal rhythms for sleep and wakefulness, independent of external illumination. The helmet visor can dim or brighten to simulate day and night on a familiar timescale, helping maintain normalcy despite the alien environment outside. These accommodations acknowledge that human biology remains fundamentally earthbound, even when technology enables presence on other worlds. During the nighttime period, exploration continues, using the suit's powerful external lights, artificial illumination that creates pools of white light in the surrounding dimness. The lights reveal details impossible to see in the faint, natural twilight, showing rock textures, regolith patterns, and surface features with clarity that daylight's orange cast obscures. Photography at night requires the artificial lighting, the cameras capturing scenes illuminated by suit lights rather than by natural skylight, creating images with strong shadows and high contrast, utterly unlike the shadowless, diffuse daytime views. These night images show Venus in yet another lighting regime. Neither the orange daylight nor the deep brown twilight, but the stark white artificial light that humans bring to dark environments. The darkness amplifies sounds, or rather the absence of sound, as Venus's surface remains absolutely silent, with no wind, no water, no life to create noise. The suit's own systems provide the only sounds: the hum of fans and pumps, the servo whir when moving, the occasional click or beep from internal systems. All these mechanical sounds transmitted through the suit structure to the ears inside. Outside the suit, nothing produces sound except perhaps the occasional thermal crack as rocks expand and contract with temperature fluctuations. or the rare impact of a micrometeorite that survived atmospheric entry, events so infrequent that hearing one would require extraordinary luck or very long waiting. The silence allows complete focus on visual observation without auditory distraction, creating an experience of pure seeing where attention concentrates entirely on what the lights reveal in the surrounding darkness. The landscape appears different at night, familiar features rendered strange by the change in illumination, shadows creating texture details invisible in diffuse daylight. Walking through the night landscape feels like exploring an entirely different world, despite traveling the same terrain visited during daylight. The changed lighting transforming perception and revealing aspects that daylight obscures. The long night period allows unhurried exploration at whatever pace feels appropriate, as the darkness persists for week equivalent time periods that dwarf the actual week available for this journey. There is no pressure to complete observations before sunset, no risk of being caught unprepared by rapidly falling darkness. Only the slow progression of barely perceptible changes in background illumination. The timescale creates a sense of timelessness, where hours pass without significant environmental change, where the landscape exists in eternal orange day or endless brown twilight, depending on the current phase of the Venusian solar cycle. The eventual return of daylight happens as slowly as its departure, the darkness gradually diminishing over many hours as the sun climbs toward the eastern horizon, its light path through the atmosphere shortening and allowing more illumination to reach the surface. The orange glow strengthens imperceptibly, the deep brown twilight transitioning through lighter browns back toward orange. The landscape emerging from dimness into the familiar diffuse daylight that represents normal Venusian conditions. The transition takes so long that detecting the exact moment of sunrise becomes impossible without instruments, the change too gradual for senses to mark a boundary between night and day. The experience of night on Venus, though brief during this week-long journey, provides understanding of the planet's rotation and its consequences that no amount of reading or data analysis could convey as effectively. The slowness becomes tangible rather than abstract. The darkness becomes real rather than theoretical. And the strangeness of a world where days last months becomes personal knowledge rather than mere fact. This experiential understanding enriches the intellectual knowledge of Venus's rotation, making the numbers meaningful through direct encounter with what they describe. And while the rotation creates the progression from day to night, the atmosphere above undergoes its own dynamics independent of the surface rotation, creating weather patterns and wind systems that operate on different timescales and create their own forms of change and variation. The atmosphere that presses down with 90 times Earth's pressure and maintains surface temperatures hot enough to melt lead is not a static envelope, but a dynamic fluid system with circulation patterns, wind systems, and weather phenomena that operate continuously above the surface. Understanding Venusian meteorology requires distinguishing between the near-surface conditions, which remain remarkably calm and stable, and the upper atmospheric conditions hundreds of kilometers above, where winds reach speeds that would destroy any structure on Earth, and where atmospheric dynamics create some of the most extreme weather in the solar system. The disconnect between surface calm and upper atmospheric violence represents one of Venus's most striking atmospheric characteristics. At the surface where the exploration occurs, Wind speeds rarely exceed a few kilometers per hour. Gentle breezes, barely strong enough to lift the smallest dust particles or create perceptible movement of the atmosphere. This calmness results from the dense atmosphere's enormous inertia, as moving 90 times Earth's atmospheric pressure requires tremendous force, and the available wind-driving mechanisms operate too weakly at the surface to create strong winds. Measurements from Soviet Venera landers recorded surface winds typically between 0.3 and 1 meter per second, about 1 to 3 kilometers per hour, comparable to a very light breeze on Earth that barely rustles leaves. These gentle winds create no significant erosion, no sound of rushing air, no perceptible cooling effect on hot surfaces. The weak surface winds arise from the minimal horizontal temperature gradients that exist at ground level. As the thick atmosphere redistributes heat so effectively that temperature differences between equator and poles at the surface measure only a few degrees, despite the equator receiving much more solar energy than polar regions. On Earth, horizontal temperature differences drive winds as air moves from high pressure over cold regions to low pressure over warm regions. But on Venus, the surface temperature uniformity removes this driving mechanism almost entirely. What little wind does occur probably results from subtle pressure variations created by topographic effects, where air flowing over mountains or descending into basins creates small pressure differences, or from thermal tides driven by solar heating of the atmosphere above. Standing in the gentle surface breeze creates minimal sensation, the slight air movement detectable only through watching how fine dust particles occasionally lift and drift, or through noticing the suit's external temperature sensors showing tiny variations as air movement enhances convective heat transfer. The suit itself affects local airflow, creating a disturbance in the otherwise still atmosphere. Warm surfaces of the suit creating weak convection currents, as the few degrees temperature difference between suit exterior and ambient air drives subtle circulation. These micro-scale atmospheric dynamics represent the smallest scales of Venusian meteorology, the personal weather created by the presence of a relatively cool object in the hot environment. Looking upward from the surface toward the cloud layers 50 kilometers above means looking toward completely different atmospheric conditions, where winds reach speeds of 100 meters per second or more, about 360 kilometers per hour, faster than the strongest hurricanes on Earth. These winds circle the planet in 4 to 5 Earth days, despite the planet itself taking 243 days to rotate, creating what scientists call superrotation, a phenomenon where the atmosphere moves much faster than the solid planet beneath it. The mechanism driving superrotation involves complex interactions between solar heating, atmospheric waves, and momentum transport, processes that remain incompletely understood despite decades of study and multiple spacecraft missions. The super-rotating winds exist primarily in the cloud layer between 45 and 70 kilometers altitude, where measurements from atmospheric probes and orbital spacecraft have mapped the wind patterns in detail. The fastest winds occur near the equator at cloud top level, reaching speeds above 100 meters per second, while wind speeds decrease toward the poles and decrease with depth below the cloud tops. At the altitude where the cloud base sits, around 45 to 48 kilometers up, winds blow at perhaps 40 to 60 meters per second, still tremendously fast by Earth standards, but significantly slower than at cloud top level. Below the clouds in the relatively clear atmosphere extending down to the surface, wind speeds continue to decrease with decreasing altitude, reaching the nearly calm conditions measured at ground level. The vertical wind profile, from calm at surface to hurricane force at altitude, creates wind shear that would generate severe turbulence if encountered by an aircraft, the velocity changing by tens of meters per second over vertical distances of kilometers. This shear drives mixing and turbulence that help redistribute momentum and energy through the atmosphere, contributing to the overall circulation patterns that transport heat from dayside to nightside and from equator to poles. The turbulent mixing also affects cloud structure and distribution, creating the features visible in ultraviolet images of Venus's cloud tops, including the distinctive Y-shaped dark markings that appear in UV but remain invisible in visible light. The clouds themselves show complex structure and dynamics, with the sulfuric acid droplets forming layers at different altitudes depending on temperature and sulfur chemistry. The main cloud deck contains the highest concentration of droplets and the thickest optical depth, completely obscuring the surface in visible light and reflecting most incoming sunlight back to space. Above and below this main deck, thinner haze layers extend the cloud system vertically, creating gradual transitions between the dense clouds and the clearer atmosphere beyond. The cloud particles circulate with the super-rotating winds, racing around the planet in 4-day cycles, individual droplets possibly making hundreds of circuits around Venus during their existence before either falling into warmer regions and evaporating, or growing large enough to fall as rain that evaporates, before reaching the surface. The rain that never reaches ground level represents one of Venus's meteorological curiosities, as sulfuric acid condenses and falls from the clouds in drops that would constitute acid rain if they survived to the surface. But the increasing temperature with decreasing altitude causes the droplets to evaporate around 30 to 40 kilometers altitude. The falling droplets create a zone of virga, precipitation falling from clouds, but evaporating in the air below before reaching the ground, similar to phenomena sometimes seen in dry regions on Earth, where rain falls from clouds but evaporates in dry air before wetting the ground. On Venus, the virga is permanent and global, a continuous rain that never lands, the sulfuric acid cycling between gas and liquid as it circulates through different temperature regimes. The large-scale circulation pattern transporting heat from equator to poles follows a structure called a Hadley cell, where air rises at the equator, flows poleward at high altitude, descends at the poles, and returns equatorward at low altitude, creating a meridional overturning circulation. On Earth, Hadley cells extend from the equator to about 30 degrees latitude before other circulation cells take over. But on Venus, the slow rotation allows Hadley cells to extend from equator to pole in each hemisphere, creating a simpler, global circulation pattern. The rising air at the equator carries heat upward and poleward, explaining how heat reaches the poles despite their receiving much less direct sunlight than equatorial regions, while the descending air at the poles compresses and warms adiabatically, further reducing the temperature difference between equator and poles. The polar regions show distinctive vortex structures discovered by orbital spacecraft, with a double vortex pattern at each pole where air spirals inward and downward in two spiral arms rather than a single circular vortex. These polar features appear in infrared images that penetrate through the upper clouds to show the circulation patterns in the mid-level atmosphere, revealing complex dynamics that atmospheric models struggle to reproduce accurately. The vortices change shape and structure over timescales of days to weeks, sometimes appearing as distinct S-shapes and other times merging into more circular patterns, demonstrating that even Venus's relatively stable atmosphere exhibits variability and time-dependent behavior. Lightning on Venus remained controversial for years, with some spacecraft reporting radio signals consistent with lightning discharges, while others found no evidence for electrical activity. The current consensus suggests lightning does occur, but perhaps less frequently than on Earth, and possibly concentrated in particular regions or atmospheric conditions. The lightning might occur in the clouds from charge separation, as droplets collide and separate, similar to thunderstorm electrification on Earth, or might occur near volcanic eruptions if such eruptions inject ash and gas into the atmosphere, creating localized regions of charge separation and discharge. Detecting lightning from the surface would require specialized equipment, measuring radio emissions, or possibly direct visual observation of flashes. Though the cloud base sits 50 kilometers overhead and might obscure lightning occurring at higher altitudes. The weather on Venus, defined broadly as time-variable atmospheric conditions, shows less short-term variability than Earth weather due to the slow rotation and strong thermal inertia preventing rapid changes. Day-to-day weather forecasting on Venus would be simpler than on Earth because conditions change slowly and predictably, with no rapidly moving storm systems or fronts creating sudden changes in temperature, pressure, or precipitation. The clouds circulate in their 4-day cycle. The winds blow steadily at each altitude. The temperature remains nearly constant, and the atmospheric pressure varies by tiny fractions of a percent, creating conditions stable enough that yesterday's weather provides excellent prediction for tomorrow's weather. This stability contrasts dramatically with Earth's chaotic and rapidly changing weather systems, representing another fundamental difference between the two planets despite their similar sizes. The experience of standing under such a massive, dynamic atmosphere while feeling almost no wind creates a cognitive dissonance. Knowing intellectually that hurricane-force winds blow overhead while experiencing perfect calm at ground level. The disconnect emphasizes how atmospheric behavior depends on altitude and how phenomena at different heights can differ completely despite occurring in the same connected fluid envelope. The atmosphere becomes not a single entity, but a layered system with distinct regimes at different elevations, each layer operating according to different dynamics and responding to different forcing mechanisms. And while the atmosphere creates the environmental conditions that define surface experience, the week of exploration draws towards its end, with the final day becoming a time for synthesis and reflection on everything observed and experienced. The final full day on Venus arrives with the same orange glow that has illuminated every day of this journey. The unchanging light a reminder of the planet's fundamental characteristics, even as familiarity with the environment has grown. This last day provides opportunity to consolidate observations, to revisit particularly interesting features within reach, and to reflect on what this week of exploration has revealed about Venus as a world and about planetary science more broadly. The accumulated experience, from arrival through exploration of plains, highlands, volcanic features, and the various aspects of the Venusian environment, combines into a holistic understanding deeper than any single observation could provide. The landscape that seemed alien and hostile upon arrival has become familiar through days of patient observation. The orange light, no longer strange but normal, the crushing pressure, and extreme heat, no longer conceptual threats but accepted background conditions that the suit manages reliably. This familiarity breeds not contempt, but appreciation for Venus's unique character, for the ways this world differs from Earth, and for the geological and atmospheric processes that created those differences. The rocks that initially appeared as generic grey basalts now reveal their individual textures, vesicle patterns, and weathering characteristics. Each one distinct once, attention focuses enough to notice the variations. The regolith that seemed uniform shows subtle color gradations and grain size distributions that tell stories about deposition patterns and source regions. The morning of this final day begins with returning to the landing site, reversing the journey outward, and following the navigation system's guidance back to the starting point. The trek back covers familiar ground now, the route traversed previously showing the same landmarks and features noted during the outward journey, though seeing them from the opposite direction provides slightly different perspectives. The volcanic plains appear unchanged, as they have remained unchanged for hundreds of millions of years and will continue unchanged for hundreds of millions more, barring catastrophic volcanic resurfacing. The timescale of geological processes on Venus operates so slowly that human observation periods remain far too brief to detect change, making the landscape essentially static within human perception. Arriving back at the landing site creates a sense of completion and closure, the journey having formed a loop that returns to its starting point. The footprints from the initial arrival remain clearly visible in the regolith, undisturbed by wind or any other process, marking the exact spots where first steps touched Venusian soil. These prints will persist essentially forever in this environment, or at least for millions of years, until volcanic burial or rare impact ejecta eventually covers them, creating a permanent record of this imagined journey that the hostile conditions will preserve better than almost any environment on Earth would preserve human traces. The final day allows time for detailed examination of features near the landing site that initial observations might have overlooked or treated superficially. Small rocks receive close attention, their vesicle patterns and weathering rinds studied carefully, mental notes made about variations in texture and color that might indicate compositional differences or different formation conditions. The regolith undergoes scrutiny, the grain size distribution estimated through visual inspection, the color variations mapped mentally, the depth estimated where small depressions or soot footprints expose subsurface material. These detailed observations represent the kind of thorough site characterization that actual surface missions would conduct, measuring and documenting everything possible about the landing site to extract maximum scientific value from limited time. The suit's instruments collect final measurements, documenting temperature, pressure, atmospheric composition, surface reflectivity, and other parameters that quantify the environment. These measurements join the continuous data stream recorded throughout the week, creating a comprehensive dataset that describes Venusian surface conditions with precision impossible from orbital observations alone. The temperature remains steady at 475 degrees Celsius. The pressure holds at 92 Earth atmospheres. The atmospheric composition shows the expected carbon dioxide-dominated mixture, all values confirming that Venus maintains its extreme conditions with remarkable stability. Comparing Venus to Earth becomes inevitable during this final day, as the week of experiencing Venusian conditions highlights both the similarities and profound differences between the two worlds. The similarities include size, with Venus's diameter only about 5% smaller than Earth's, and bulk composition, with both planets consisting primarily of silicate rock mantles surrounding iron-rich cores. The orbital distances from the Sun differ by only about 40 million kilometers, placing both planets in the inner solar system, where temperatures allow rocks to exist in solid form. The gravitational accelerations at the surface differ by only about 10%, creating similar conditions for geological processes and atmospheric retention. The differences, however, overwhelm the similarities in importance for surface conditions and habitability. The atmospheric mass on Venus exceeds Earth's by a factor of 93, creating the crushing surface pressure that makes liquid water impossible and that traps heat through greenhouse warming. The atmospheric composition, nearly pure carbon dioxide on Venus compared to nitrogen-oxygen on Earth, reflects completely different evolutionary paths for the two atmospheres. The absence of a magnetic field on Venus leaves the upper atmosphere exposed to the solar wind, allowing atmospheric escape processes to operate that magnetic fields prevent on Earth. The slow retrograde rotation creates the unusual day-night cycle and affects atmospheric dynamics in ways that rapid prograde rotation does not. The runaway greenhouse effect that created Venus's current climate represents perhaps the most important difference, as this process transformed what might have been an Earth-like world with oceans and moderate temperatures into the scorched desert that exists today. The greenhouse effect operates on both planets, with atmospheric gases absorbing infrared radiation emitted by the surface and trapping heat that would otherwise escape to space. But on Venus, the effect ran to completion, while on Earth, it remained moderate. The difference likely relates to the initial water inventory and the distance from the Sun, with Venus's slightly closer orbit receiving about twice as much solar energy as Earth, enough to evaporate more water into the atmosphere, where it enhanced greenhouse warming, which caused more evaporation, creating a positive feedback that continued until the oceans evaporated completely. The water vapor in the hot atmosphere then dissociated under solar ultraviolet radiation, breaking H2O molecules into hydrogen and oxygen, with the light hydrogen atoms escaping to space, while oxygen reacted with surface rocks. Over hundreds of millions of years, Venus lost its water to space and to chemical reactions, transforming from a potentially habitable world with oceans to the dry, scorched planet that exists now. The loss of water allowed carbon dioxide to accumulate in the atmosphere, since water is necessary for removing CO2 through weathering and carbonate formation. And without water, this removal mechanism ceased, and volcanic outgassing added more CO2 over time, building to the current thick atmosphere. This climate history provides cautionary lessons for Earth, as it demonstrates that greenhouse effects can become self-reinforcing under certain conditions, and that planetary climates can transition between different stable states. Earth currently maintains a relatively stable, temperate climate through complex feedbacks involving water cycle, carbonate-silicate cycle, and biological processes. But perturbations to these systems could potentially trigger transitions toward different climate states. Venus's fate represents an extreme outcome that Earth is unlikely to replicate, given the differences in solar energy input and current atmospheric composition. But understanding how Venus's climate evolved informs understanding of Earth's climate system and its responses to forcing changes. The absence of plate tectonics on Venus represents another major difference, with significant consequences for geological evolution and atmospheric composition. Earth's plate tectonics constantly recycles crust through subduction, carries volatiles from atmosphere and ocean into the mantle, generates volcanism at mid-ocean ridges and subduction zones, and creates continental crust through complex magmatic processes. Venus lacks these processes, instead resurfacing through episodic volcanic events that occur perhaps every few 100 million years, with long quiet periods between major eruptions. This difference in tectonic style affects how heat escapes from the interior, how volatiles cycle between surface and interior, and how crustal composition evolves over time. The reasons Venus lacks plate tectonics remain debated, with hypotheses including the higher surface temperature making the lithosphere too weak to subduct, the absence of water in the crust preventing the lubrication that water provides for subduction on Earth, or the different thermal evolution creating conditions unfavorable for plate boundary formation. Whatever the cause, the consequence is a planet that operates geologically in a fundamentally different mode than Earth, with implications for everything from volcanic activity patterns to atmospheric evolution to surface age distribution. Understanding these differences helps planetary scientists comprehend the range of possible tectonic regimes and how they depend on planetary characteristics like size, composition, temperature, and volatile content. The week on Venus has provided experiential understanding of these differences that textbook knowledge alone cannot provide, making abstract scientific concepts concrete through imagined direct encounter. Standing in 90 atmospheres of pressure makes the greenhouse effect real rather than theoretical. Experiencing the orange light makes atmospheric scattering tangible. Walking across ancient lava flows makes geological timescales personal. This experiential dimension enriches intellectual understanding, creating connections between concepts and sensory experiences that memory preserves more effectively than pure abstraction. The final evening on Venus arrives with the same gradual dimming that marks every Venusian sunset. The orange glow slowly fading toward deeper tones as the sun's position relative to this location shifts toward the western horizon. The suit's systems continue their reliable operation, never faltering, despite days of continuous work in extreme conditions, a testament to the engineering sophistication required for surviving in such environments. The power reserves show adequate capacity for the ascent back through the atmosphere. That will occur tomorrow. The consumables remain sufficient. The structural integrity shows no degradation. All systems reporting normal status as they have throughout the journey. The night brings rest and preparation for departure, the final sleep period on Venus's surface before returning to orbit and then to space beyond. The landscape settles into its eternal routine, unchanging, patient, indifferent to human presence. The week has allowed observation and understanding, but Venus remains fundamentally unchanged by the visit, its processes continuing as they have for billions of years, as they will continue long after this imagined journey ends. The ascent begins with final checks of the suit's systems and a last look at the landscape that has been home for a week. The orange-lit plains extending to the hazy horizon in all directions under the thick clouds that never part. Leaving the surface requires different preparation than arrival, as the ascent vehicle must overcome Venus's gravity and atmospheric drag to reach orbit, though in this thought experiment, the specific technology enabling departure matters less than the experience of leaving and the perspective gained from watching Venus recede. The separation from the ground occurs smoothly, the suit's weight transferring from the solid rock to whatever propulsion system provides lift, the landscape beginning to drop away below. The first 100 meters of ascent show the landing site shrinking beneath, the footprints remaining visible as small marks in the regolith. The rocks and features that became familiar through days of observation becoming less distinct as distance increases. The horizon extends farther as altitude increases, revealing terrain beyond what was visible from the surface. The curvature of the planet beginning to appear as the viewpoint rises above ground level. The orange light persists at low altitudes, the thick atmosphere continuing to create the characteristic color and diffuse illumination that defines surface conditions, though the exact shade shifts slightly as the viewing geometry changes. Rising through the first few kilometers of atmosphere shows the landscape spreading below like a map. The volcanic plains visible to greater distances, the highland regions that were visited appearing as slightly rougher terrain rising above the smoother lowlands. The trek route might be visible as a faint line of disturbed regolith, if viewing angle and lighting permit, though the atmospheric haze likely obscures such small details even from modest altitude. The scale of Venus becomes more apparent from elevation, the landing site representing an infinitesimal fraction of the planet's surface. The week of exploration having covered perhaps a few dozen kilometers of the hundreds of millions of square kilometers that constitute the full planet. Continuing upward through 10 and 20 kilometers altitude, the temperature begins to decrease measurably as the altitude increases and the greenhouse effect weakens with height. The pressure also drops, though even at 20 kilometers altitude, the pressure still exceeds 10 Earth atmospheres, the thick atmosphere extending to great heights before thinning significantly. The orange color of the sky perhaps lightens slightly or shifts in hue as the atmospheric path length to the surface increases and the viewing geometry changes, though the clouds still lie 30 kilometers above and continue to dominate the optical properties of what appears overhead. Approaching 30 kilometers altitude marks reaching the base of the cloud layer, where sulfuric acid begins to condense from vapor into tiny droplets that create the haze, transitioning into denser clouds above. The visibility begins to decrease as the cloud particles scatter light more intensely than the relatively clear atmosphere below, creating the beginning of the milky obscuration that completely hides the surface from space-based observers. Looking downward shows the surface beginning to disappear beneath the gathering haze, features becoming indistinct and blurred, the orange plains fading into uniform brightness without clear details. The last view of the surface shows only generalized brightness variations, suggesting topography, but revealing no specific features. The landscape vanishing into obscurity as the clouds close in. Entering the main cloud deck between 48 and 70 kilometers altitude immerses the ascending spacecraft in the thick sulfuric acid aerosol, the visibility dropping to near zero. Only bright milky glow visible in all directions as light scatters from countless cloud droplets. The temperature here drops to around -10 to -30 degrees Celsius, cold enough that any exposed surfaces would quickly frost over with sulfuric acid condensate, though the suit's environmental systems prevent exposure. The pressure continues to decrease with altitude, dropping below 1 Earth atmosphere around 50 kilometers up, and continuing to decline rapidly with further ascent. The winds increase dramatically with altitude, reaching the hurricane force speeds of the superrotation. Though the smooth flow prevents strong turbulence if the ascent trajectory aligns properly with the wind direction. Breaking through the cloud tops, around 70 kilometers altitude, produces a dramatic transformation. The milky white cloud deck giving way suddenly to clear space above, stars becoming visible for the first time since entering Venus's atmosphere a week earlier. The sun appears as a brilliant point of light rather than diffuse glow, harsh and direct after days of seeing only scattered orange illumination. The cloud tops stretch below like a white blanket covering the entire planet. Featureless in visible light, though showing the characteristic Y-shaped patterns in ultraviolet wavelengths that reveal atmospheric dynamics invisible to the human eye. The beauty of the view contrasts with the hostility of the environment below, the clouds appearing soft and inviting while hiding the scorched surface beneath. Ascending through the upper atmosphere above the clouds shows the sky darkening toward black as the tenuous gas thins and space conditions emerge. The stars grow brighter and more numerous as the obscuring atmosphere falls away. Familiar constellations appearing in their correct positions, the celestial sphere becoming visible after being hidden throughout the surface stay. Venus itself appears below as a crescent or gibbous disk, depending on the angle between spacecraft, planet, and sun. The phase determined by the relative positions, just as Venus shows phases when viewed from Earth. The clouds show their global circulation patterns from this perspective. The 4-day rotation visible through time-lapse observation, showing how atmospheric features move from equator to pole and around the planet. Reaching orbital altitude around 300 kilometers above the surface creates stable conditions where the spacecraft can circle the planet without further propulsion. Though the thin upper atmosphere at this height creates slow drag that would eventually decay the orbit without periodic boosts. From orbit, Venus appears as a world-sized object rather than infinite landscape, the curvature obvious, the terminator line between day and night visible sweeping across the cloud tops, the planet's spherical nature apparent in a way impossible to perceive from the surface. The perspective shift from surface to orbital changes understanding fundamentally, the local surface experience giving way to global planetary view. Details disappearing, but large-scale patterns emerging. The orbital vantage allows appreciation of Venus as a planet among planets, similar in size to Earth and hanging in space as Earth does, both worlds bathed in sunlight and surrounded by atmospheres, yet so different in their surface conditions and habitability. The comparison becomes visual rather than abstract. Seeing Venus whole and knowing what lies beneath the clouds from direct experience creates understanding different from knowing the same facts without visual and experiential context. The clouds hide the harsh surface, perhaps mercifully, presenting Venus to the universe as a beautiful, if mysterious world. The reality of conditions below remaining secret except to those who penetrate the veils of sulfuric acid and dense carbon dioxide. The time in orbit provides opportunity for final observations and documentation, photographing the planet from various angles, recording the cloud patterns and atmospheric dynamics, watching how the Terminator moves across the globe as Venus rotates beneath. The slow rotation becomes apparent from this perspective, as features tracked over hours barely shift position. The long Venusian day manifest in orbital observations. The lack of moons means Venus hangs alone, no satellites accompanying it in its orbit around the Sun, no nearby companions like Mars's Phobos and Deimos, or Jupiter's Galilean moons. The solitary nature emphasizing Venus as an isolated world. The journey concludes not with answers to all questions, but with deeper appreciation for what Venus is and why it matters for planetary science. The week spent experiencing Venusian conditions, though imaginary, drew from real data and real physics, every detail grounded in measurements and observations from actual spacecraft and landers. The crushing pressure, the extreme heat, the thick clouds, the volcanic plains, all these aspects exist as described because missions confirmed them through direct measurement. The thought experiment of visiting Venus personally transforms those measurements into experiences, making the abstract concrete and the numerical personal. The value of this mental journey lies in creating understanding through simulated experience, allowing the mind to construct models of Venus reality that pure data alone might not provide. Standing on Venus's surface, even imaginatively, creates memory structures that preserve facts more effectively than reading specifications, associating information with sensory details and spatial contexts that human memory evolved to handle. The orange light becomes linked to atmospheric scattering mechanisms. The crushing pressure connects to greenhouse physics. The ancient lava plains relate to planetary resurfacing processes. All these connections strengthened through narrative and imagined experience. Venus continues its orbit around the Sun, completing the circuit every 224.7 days, while rotating slowly backward on its axis, the clouds racing around in 4-day cycles, the surface baking under the greenhouse effect. All these processes continuing whether observed or not. The hundreds of millions of square kilometers of volcanic plains and highland Tessera remain largely unexplored except through orbital radar mapping, their details unknown, their rock compositions uncertain beyond the few landing sites where Soviet Venera landers made brief measurements. Future missions might return to Venus with more capable landers or even rovers exploring the surface in reality, as this thought experiment explored it in imagination. The lessons from Venus inform our understanding of Earth and of planetary climate more broadly. The greenhouse effect that creates moderate warmth on Earth operates in extreme form on Venus, demonstrating how atmospheric composition and solar energy input determine surface temperature. The role of water in moderating climate and enabling plate tectonics becomes clear through its absence on Venus, and the consequences that absence creates. The importance of magnetic fields for protecting atmospheres shows itself in Venus's atmospheric loss to space over billions of years. Each comparison point between Earth and Venus refines understanding of what makes planets habitable and what factors push them toward extreme conditions. The beauty of Venus, real despite the harshness, deserves recognition alongside the hostility. The orange light creates its own aesthetic, the diffuse glow painting landscapes in warm tones that would be lovely if they were not accompanied by lethal heat and pressure. The clouds appear beautiful from orbit, brilliant white against the black of space, their patterns and circulation creating dynamic visual interest. Even the crushing pressure and extreme temperature represent nature operating according to physical law, the greenhouse effect functioning exactly as physics predicts, the atmosphere behaving as fluid dynamics requires. There is beauty in this consistency, in the way Venus follows the rules of planetary science predictably and reliably. Leaving orbit for the return journey to Earth would involve firing engines to escape Venus's gravitational pull and transferring to an Earthbound trajectory, watching Venus shrink behind as distance increases. The planet would pass through phases visible from the departing spacecraft, appearing gibbous, then half-illuminated, then crescent, as the angle changed with increasing distance. Eventually, Venus would appear as a bright star again, the individual planet shrinking to a point of light, indistinguishable to the naked eye from its appearance from Earth. Though memory would hold the knowledge of what that point represents, the scorched world beneath eternal clouds where this week of exploration occurred. The experience, though entirely hypothetical, leaves its mark on understanding and appreciation. Venus becomes familiar rather than alien, known rather than mysterious, understood through simulated direct encounter rather than remaining abstract. The facts about pressure and temperature and atmospheric composition transform from statistics into experiences, remembered not as numbers, but as conditions felt and observed. This transformation represents the value of thought experiments in science education and understanding, creating pathways to knowledge that bypass the limitations of direct experience while approximating some of its benefits. And so, the journey concludes, having traveled from arrival through exploration to departure. Having stood on Venus and walked its plains and climbed its highlands and examined its rocks and atmosphere and light, all in imagination, but all grounded in reality. All impossible physically with current technology, but possible mentally through knowledge of what Venus is and how it works. The week on Venus ends, but the understanding gained and the appreciation developed persist, carried back to Earth, where looking up at the bright evening star in the twilight sky brings knowledge that beneath those brilliant clouds lies a world explored thoroughly and understood deeply through this imagined journey. Beneath the orange sky, across ancient lava, under crushing pressure and extreme heat, where the stillness and the harshness and the beauty all exist together on the second planet from the sun.